السلام عليكم، مساء الخير يا شباب. هل الصوت واضح؟
واضح يا باشمهندس.
طيب دقيقتين بس كده العدد بس يزيد شوية وهنبدأ على طول دقيقتين بس. أظن كده بقى إحنا انتظرنا والعدد بقى كويس. يعني خلاص تخطينا ال30 كافي بقى الناس تخش بقى تكمل معانا. إيه الأخبار؟ جاهزين لليوم الثالث؟ متحمسين؟ نبدأ بقى الكوانتم ماشين ليرنينج. ماشي، يوسف معانا أهو جاهز. ندى جميل جدا. بقية الناس فهد، يوسف كويس، عاش، حسن، ناس متحمسة خلاص. عايزين بقى كده ندي تحية كويسة للدكتورة نهيلة والدكتور وليد، اشرحوا لنا النهاردة كوانتم ماشين ليرنينج. هنبدأ بقى الرحلة بتاعتنا كويسة بقى، نشفت من امبارح من الكلاسيكال النهاردة بقى كوانتم. هنكمل بكرة وبعده في الاوبتمايزيشن وفي الكيمستري. أرجو بقى إن أنا يكون صوتي واضح، وأنا يعني لو قعدت أتكلم شوية كده أعرف الدكاترة هيبقى صعب عليا إن أنا أوفيهم حقهم. فأنا هسيب بقى دكتورة نهايلة تعرف نفسها وتبدأ في السيشن، وبعد كده هناخد بريك زي ما احنا متعودين من 7:30 لحد الساعة 8. بعد كده نرجع لللاب مع باشمهندس وليد وباشمهندس عبد الرحمن. اتفضلي يا دكتورة نهيلة لو جاهزة.
شكرا. Let me just start sharing my screen first. Okay, my screen is visible, right?
مظبوط يا دكتور، اتفضل.
Okay. Yeah. So hi everyone. Thank you for the invitation first. So yeah, let me start by introducing myself. I'm Nouhaila Innan, and right now I'm a postdoc and research team lead at April Lab and Center for Quantum and Topological Systems at New York University, Abu Dhabi campus. And I'm working mainly on quantum algorithms and quantum machine learning. Okay, I think there is. أنا بتكلم عربي بس أنا من المغرب, so if I start speaking Arabic I don't think anyone can understand me, so I would prefer to switch to English. Sorry.
براحتك يا دكتور، مفيش مشكلة لو حابة يعني مفيش مشكلة، براحتك خالص. حابة نجرب الأول ماشي برضه مفيش مشكلة.
Yeah, I don't know, it's difficult to speak just proper Arabic, عربية فصحى instead of the region
لا
مغربي.
لا لا، ما نقصدش كده باللهجة المغربي، بس فعلا أظن ممكن الأغلب بقى ما يفهمش أو كده.
But yeah, so yeah, I have PhD in quantum machine learning. I defended my thesis last year in August, so it has been a year I'm working on here as a postdoc. So today I will give a lecture or a talk about quantum machine learning introduction. So I keep it very basic. I won't go into the details of mathematics and equations. So yeah, we can start. Let me. Okay. So directly we start with the historical context and developments of QML, how it started. So the history of QML, as outlined here, trace as remarkable trajectory of theoretical and practical advancements in quantum computing. So this timeline begins with Max Planck foundational hypothesis on quantized energy levels in 1090. Then it's marking the inception of quantum theory. Then it's progressed through the critical milestones such APR paradox in 1935 and the Bell inequality in 1964, which challenged and tested the fundamental promises of quantum mechanics. Then this early development led to the groundwork for understanding quantum entanglement, which is a pivotal concept for quantum computing and definitely for quantum machine learning. Then in the years of 1970, it saw the birth of quantum information theory, which is a crucial framework for quantum computing and QML. So it started with Richard Feynman in 1981. He proposed the simulating quantum system, which led to cornerstone for developing QML algorithms or any just quantum algorithms. Then also the discovery of topological quantum order in 1982 hinted at novel methods to improve the qubit stability, which is development on the hardware part. Then started developing algorithms like Shur in 1994, which demonstrated the potential of the quantum computers to factor large numbers efficiently, showing the powerful capabilities that quantum computing could harness. Then there is in early 2000, there is the foundational concept that will later serve quantum machine learning, such quantum neural network models and quantum associative memory. It was just very theoretical, and to think how we can integrate quantum in the machine learning. Then there is the application phase of quantum computing began to materialize with Altesky quantum perception model, which is was the first model, quantum machine learning model in 2001. But yeah, it was very theoretical. Then the execution of Shor algorithm on a quantum device, all of those helped to build the quantum machine learning field. So quantum machine learning as a field officially began in 2015 with Maria Scholl. I think everyone, I'm not sure if everyone knows Maria Scholl, but yes, she contributed a lot to quantum machine learning. Then a significant progress after that has been made in developing various quantum algorithms and models. Also, IBM introduction of cloud quantum computing, I think in 2016. Also, like the access to quantum resources, accelerating research like such Qiskit. And in recent years, QML has extended its reach into diverse fields like drug discovery, high energy physics, healthcare, finance, and biology. So instead of having just like developing algorithms right now, you can see that it's like we are targeting real world application like fraud, some like cancer detection, this kind of application. So this advancement reflects like quantum machine learning growing importance and application birds, supported by leading companies like IBM Quantum, Xanadu with Penelane, D-Wave, Rigetti, Ionic, Amazon, like different companies. And with this ongoing advancement, it suggests that this is like, I would say, a promising future where quantum machine learning will continue to solve some potentially complex computational problems and offer new insights across various domains. So this is how quantum machine learning started. Now moving, what does exactly quantum machine learning means? So QML is a cutting-edge research area that explores the interplay of ideas, concepts, techniques from quantum computing and machine learning. It's kind of like 50% of machine learning, then 50% of quantum mechanics and quantum information, quantum computing. So the idea started like to aim to leverage the unique properties that we have in quantum mechanics, like superposition, entanglement, to enhance the capabilities of the traditional machine learning algorithms. This might sound like complex, but like we can break it like into down simply. So as you see here, it starts with the qubits. The qubits are like the basic units of quantum information, like bits in classical. This is how we represent the information. In quantum, we use like qubits. Then these qubits, they are like represented in a Bloch sphere. So this is like the space solution that we have. And to manipulate means like to do the calculation, we will just like change the direction of those qubits inside these quantum blocks. That's why we have the quantum gates. And this quantum gates like change the state of these qubits. Think of them as operation that only quantum hardware or like simulator can use. Then these quantum gates combine to form like a quantum circuit, which are like sequence of these operations, quantum gates, working together to perform complex calculation. Then we have those circuits help us build our quantum machine learning models, which are like tools or models that can learn from data, just like classical AI or classical machine learning. But yeah, the difference is like learnable or trainable parameters. So if we make this quantum circuit parameterized, means it has some parameters, then we have the quantum machine learning. Sorry. Then here on the left side, this is what we call like a matrix that illustrates the different combination of data generating system and data processing devices. So we have, this is the first one, like classical to classical. Both the data generation and processing are done using classical systems. This is the traditional approach used in machine learning, as explained, I think, yesterday. Then here we have this either like classical quantum data is generated using classical systems, but proceed using quantum devices. Then we have either like quantum classical. So the data is generated using quantum systems, but proceed using classical devices. This combination, both combination is like, it's the same, just instead of using the device, we will use a quantum computer, we will use the classical computer. And we have this when the data generation processing both are done using quantum systems, which represent like the full potential of QML. But right now, at this stage, we don't have yet this, because like if we are talking about quantum data that comes like from quantum experiments, it involves like the quantum sensors and a lot of things. We are not yet at this stage, but what we do is like we break it. So we have this classical data from sensors, from any like just like normal classical data. We encode it, and I will explain that later in details, to quantum state. So we can have like, this is the quantum data, and also we use a quantum device or quantum hardware. Yes, moving now, what makes quantum machine learning quantum? So to qualify as QML, there is two primary criteria that must be met. So the first, the algorithm itself runs on quantum hardware. So this is like the ideal case, but like most of the time you are using simulator, so this is fine. But this means that the computational process and operation are executed on the simulator or hardware. Then the second part that I just explained, and I will explain in details because there is like different techniques, is the data it operates on is quantum or comes from quantum state process. So this implies that the data being processed is quantum.
I didn't understand that.
Sorry. Yeah. Let me just switch off my phone once again. Yeah, sorry about that. So yeah, the second part is the data itself. So as I explained, it must be like comes from a quantum state or process, or we encode it. And yeah, and the right side, this is like how the structure of like, this is from IBM quantum computer. So this is the quantum computer, and this is like where the quantum ships, which has like access to the qubits, is here. So now we will move how QML works. Very similar to classical machine learning, we have the data preparation. So just like we start with the classical data, and there goes into pre-processing, feature engineering, very the same process as the classical. So here we make it like suitable for quantum processing. And this is also very crucial for preparing the data and extracting the relevant features, because sometimes we have a limited number of qubits. So we can, if we have a data with like 100 feature, we need to make sure that we cannot use this 100. So maybe we will do some dimensionality reduction using PCA or like other techniques. Then the second part, which is like the most important, or like I would say the first step into QML, which is the data encoding. So the processed data is then encoded into quantum state, and this involves mapping the classical data into a quantum system using specific encoding techniques, and I will discuss like a couple of techniques. Then this encoded data is now represented as quantum state and ready for further processing by quantum algorithms. Then after that, we have the quantum gates, or like we called it like parameterized circuit or ansatz. And this is the core of the QML model. So this circuit, it consists of a sequence of quantum gates, as explained in the previous slides, applied to the quantum state, and this gate manipulates the data by trying to leverage the quantum properties like superposition when we are using Hadamard gate, and entanglement using synod gates, and controlled rotation to perform some complex transformation. Then after that, we have the measurement. So we measure the quantum system to extract the output. And the measurement collapse the quantum state into classical values, which are then used for further analysis or decision making. Then, of course, there is the loop. So we have some iterative refinements. So the model undergoes iterative refinement where the parameters of the quantum gates are adjusted to minimize the cost function. This iterative process continues until the model converts to an optimal solution. It's the same as the classical. So because this is, even right now, we say like quantum machine learning, but it's not fully quantum because of this part of optimization. We do it like classically. But however, this gradient themselves, they come like from the quantum side, but like using the parameter shift rule, which is like a very important step in QML. But technically we don't use it because it's integrated in the calculation, and whatever platform or quantum programming languages we use, it's like integrated. But yeah, I will explain that in details as well. Now moving to the data encoding. So there is like different data encoding parts. So there is the basis embedding. We say like embedding or encoding, both are fine. So I will explain this later in details. The same with this one, because like basis encoding, amplitude encoding, and angle encoding, like they are most used one and like very popular or common. And I will explain them later in details. Then we have others, like this is quantum random access memory. So we can directly store the information of the qubit state using some classical addresses as index. Then we have this Q sample. It's kind of like associates a real amplitude vector with a classical discrete probability distribution. Then it can be considered like as hybrid case of basis or amplitude encoding. Because usually amplitudes represent the encoded information, but the features are encoded in the qubit themselves. Then we have this, quantum polynomial time embedding. In short, like we use IQP. So this is composed of like a set of gates, like Hadamard rotation gates that encodes the product between the features. There is also the quantum approximate optimization embedding. So this is like employs like the ansatz. And the main advantage is that it supports the gradient computation with respect to both the features and the weights. Then we have like a Hamiltonian embedding that encodes the features into the values of the Hamiltonian operator matrix. I know this is like, it might sound like very difficult, but technically most of those techniques are like, there is the pre-built function, so you can just use it as it is. Like you don't have to worry about like how to do that. Yeah, but the thing that I want to clarify is like, there is the quantum approximate optimization algorithm. I think you might, with Ziad and Nada, they might explain it tomorrow. And there is this quantum approximate optimization embedding. So it caused a lot of confusing. They said, okay, this is an optimization algorithm, how it can be like an encoding method, but it's not the same one. So here we use, so the quantum approximate optimization algorithm, it's used for solving optimization problems. But here it's like a feature embedding circuit that just like takes the inspiration from the structure, and it works like we start like with our input features, then are encoded into qubits through rotation. Usually we use like rotation X or gates. Then this features encoding moves like, then we have each layer of the embedding as like a variational ansatz consisting of two elements. We have like two qubits interactions with implemented with multi-rotation Z gates. Yeah, but yeah, this details, it doesn't matter because like it's good to know, but most of the time you will use it like just like as a pre-built function, unless you want to customize it, and it will be later. At the beginning, you just start with the pre-built functions. Then there is also the Hamiltonian embedding. So here, like, it's very simple, like just like you use it as like you try to represent the features as Hamiltonian and try to encode them. There is also this displacement embedding. You just like to try to switch it a little bit, then have like a proper encoding. But yeah, this is sometimes, like I would say, which one is better? It depends. We cannot generalize in quantum. Sometimes you keep trying until you figure out, okay, this is good. Sometimes you even think about like proposing or suggesting a novel encoding method based on the constraints, because like some of them they use a lot of qubits to represent the data, and some of them they use less. So it depends. If I have like 100 feature, maybe I will think about like something and I need to use them all. Maybe I will think about using a method that doesn't use all the 100 qubits. But yeah, this is the first step into QML, and you need to do it like very, I would say, correctly, but I will explain the challenges into this. But yeah, as I mentioned, so most of the time we are starting with this basis embedding, amplitude embedding, and angle embedding. So I will explain them in details. So yeah, basis embedding is like, it involves representing real numbers as binary numbers, which are then mapped to quantum systems. It's very simple. So it allows us to use the binary nature of quantum bits, or like qubits, to encode the classical data into quantum systems. To illustrate, so consider we have the number 2. In classical computing, this number is represented in binary as 1, 0, right? So when using basis encoding in quantum computing, this binary representation is directly translated to the quantum state, 1, 0. So it's very simple, where each qubit of the binary number corresponds to a qubit in the quantum state. And the precision of this binary representation significantly impacts the accuracy and efficiency of quantum computations. Higher precision achieved like through more qubits and allows more accurate representation of real numbers, which is crucial for complex calculation in quantum algorithms. But this is very consuming from the number of qubits. Then we have amplitude encoding. This is like it's good because it has some significant advantage. So it enables us to represent multiple data values within a single quantum state. So this is achieved by encoding the data into the amplitudes of a quantum state. It allows us to use the full potential of quantum superposition. For example, here in this representation, this state C can be expressed as like a superposition of basis states, where each basis state is weighted by a specific amplitude. And mathematically, if we have a data vector x, we normalize it to ensure the sum of the square of the amplitudes equals 1. Then we have the quantum state is then represented as this equation here, where each x is like represented the amplitude corresponding to the basis state. And I mentioned that, yeah, there is some advantage of using amplitude encoding. It's particularly powerful as it allows us to compactly represent large datasets into the amplitude of a few qubits, specifically 2 power n. So it means that if we have like 16 features, we can represent them only on like square root of 16, which means like 4 qubits. That's why sometimes it's good to use, if we have like more qubits, we can use amplitude encoding. But yeah, it depends. Like I tried like, based on my experience, I work like with different encodings. I cannot say that this one is better than this one. It depends on the model that you are using, like the data set, the problem that you are trying to solve, a lot of factors. Then the last one is Engel encoding. This one is like most used. I think most of the article, at least, this starts with the Engel encoding. It's an efficient quantum data
نوهيلة،
encoding. Yes.
في حد بس عنده سؤال.
Yeah, sure.
Okay, so my question is, I select the feature and then I use this method for training the quantum, or before that I have like maybe we say like 4 qubits.
Yes. So for example, let me make it like very clear. So you have your data. It has like, for example, maybe, yeah, let's take Iris, for example. Iris is the flowers like data set. It has like 4 features and like I think around like 150 data samples. So this is the data set. I do the pre-processing, like just like labeling, coding, and also like the feature encoding, everything. This is done classically. Once I have like the X and Y, the features and the label, this is the data ready for using into quantum machine learning model. So here, it depends. If I have access to 4 qubit, good. I can use Engel encoding, and I will encode each feature into a qubit using rotation. Okay, this is like, for example, rotation Z. This is here, like, for example, take in the right figure. So here, this is the first feature. For example, 0.1. Then the second feature is 0.2. The third feature is 0.3. And the fourth feature is 0.4. This is how it looks. But if I have, for example, I have like 16 features and I have only 4 qubits, I cannot use that. So I have like 2 solutions. Either use Engel encoding, amplitude encoding, where I will encode like 4 features into 1 qubit, or I will just do some pre-processing, like try to reduce like maybe PCR, like select K best. I will choose from the 16 features that I have only 4 and use Engel encoding or any other techniques.
Okay, so that won't affect anything, like if I choose like to reduce any features?
It does, of course, like, you know, like it's like classical. Of course, there is like a trade-off. That's why you keep trying. Maybe you will lose like some, of course, like some information, and that will affect like the model accuracy and the performance. But you keep trying. Sometimes like the data, it's not that, I don't like, the model doesn't need all the features to make the decision. For example, for classification, if we are taking fraud detection, for example. So this, usually the fraud data set, they have like the ID, the number, the time, amount, and a lot of details. Sometimes it's not necessary to have all these details. We can just remove them. But if we remove an important features, definitely it will reduce the performance of the model. So which one to use? This is like just done classically. So sometimes you just like compact them into like using like principal component analysis. And sometimes there is like in scikit-learn, like machine learning libraries, there is something called like select K best. So usually this algorithm try to choose the best, like, for example, I want like top 5 features that somehow are correlated into like with the label that we have. For example, like they are very important to make the decision for this, for example, classification. So I choose them. But yeah, this part is done classically. It has nothing with quantum. Of course, sometimes if we have like access to more number of qubits, it's better to use the full data set with all the features.
Okay, I got it. Thank you. Thanks
Well,
for answering me.
you are welcome. So yeah, so I was explaining Engel in coding. Yeah, sorry.
هو بس لو حد تاني عايز يسأل عشان بس الدكتورة مش شايفة الشات، فممكن تقدروا تفتحوا المايك كده تستأذنوا، بس يبقى في فاصل في الكلام، ما نخشش في نص الكلام، واسألوا براحتكم. والدكتورة مشكورة متقبلة بقى السوبربوزيشن بتاع اللغة ده، يعني لو مش عايز
Yeah,
تسأل
of course.
بالإنجلش براحتك، اسأل بالعربي.
Yeah, يمكن تسأل
اتفضل يا
بالعربي.
دكتور،
It doesn't.
شكرا، اتفضل.
Yeah. So for Ingal encoding, as I explained, it's here like it's very simple. So we use the rotation, sometimes Z, sometimes Y, sometimes X. It depends. There is no rule. And we just like encode the feature. So usually this rotations has the angles, the parameter, and this parameter it represents the feature. Yes, then moving to parameter shift rule. So as I explained, it's related to the training part, like the optimization and how the optimization is done. So first of all, what does this parameter shift rule mean? So it's a method that computes exact gradients of the quantum circuits. So instead of like struggling with derivatives like of quantum gates directly, we evaluate the same circuit at two different parameter values. So one shifted forward and the one shifted backward. Because like technically we don't have this back propagation in quantum. So that's why there is like this parameter shift rule. So, and by combining these results, we obtain the gradient. And this make it like possible to use the gradient-based optimization methods in quantum machine learning. Without this, we cannot use the classical optimizer. Then, yeah, why do you use it? This is like I explained. So usually the gradients are the backbone of optimization, just like in classical deep learning, we use the back propagation to update the parameters. In quantum machine learning, we also need those like to gradients to train the models, any models, like any QML models, even sometimes like the quantum algorithms. Then, yeah, now one might ask, like, why not use just like finite differences? So, like we do in classical. So the problem is that finite differences like requires like a very small shift in parameters, which sometimes or like most of the time leads to numerical instability and noise on hardware, or even sometimes like if you model the noise. So this parameter shift rule avoids this by providing the analytic gradient that works reliably on quantum devices or simulator. Now, how does it work? So let's consider, yeah. So this is like a polyrotation gate of the form. And usually for such a gates, the derivative of the expectation value is usually, as you see here in the right side, can be written as this function. And notice that this formula looks like almost identical to the derivative of which can also be expressed as the difference of shifted sign function. So the crucial point here is that we don't need a new circuit. We simply run the same circuit twice at shifted parameter values and subtract the results. So yeah, and this is, let me try to connect it to this figure. So here in the left, in the right, you see the numerical gradient approach. Here we try to approximate the slope using a very small shift d theta. And this is approximate, prone to numerical errors and very sensitive to noise. On the right side, like the other one, the green, you see the analytic gradient from the gradient shift rule. So instead of the tiny shifts, we use finite shifts of like pi. And this gives us like an exact expression of the gradient. And this is where the Pauli gates example comes in. So for Pauli rotation gates, the commuter-like structure allows us to rewrite the derivative exactly in this form. So in practice computing, I would say the gradient just like means running two versions of the circuits, of the same circuit. One with theta plus pi divided by 2, and the other one is like theta minus pi divided by 2. Yeah. So the takeaway is that the parameter shift rule is the reason gradient-based optimization is feasible in quantum machine learning. It's efficient, hardware-friendly, and one of the most widely used techniques in variational quantum algorithms. So this is like, you don't have also to worry about that because usually we don't do it manually. Even in the coding, it's integrated. But it's good to know why we have this and or how we apply it or how does it work. Now moving to the algorithms. So there is like the fully quantum machine learning and there is the hybrid quantum machine learning. Right now, as I mentioned, with this backpropagation, I would say we don't have fully, but even the hybrid has like two definitions, and I will explain that. That's why sometimes even if we just say quantum machine learning models, it's not totally fully, but it's not hybrid as well. Because like hybrid, it means we involve some classical layers, and sometimes, most of the time, there is some classical layers. But yeah, I will explain in details. So there is the quantum optimization problems. This is like, I would say, not really quantum machine learning. So it depends. Some say, okay, it's also quantum machine learning, but others say no. But yeah, optimization is very different from machine learning task. But yeah, I can just like briefly explain a couple of algorithms or just mention. I think tomorrow they will give more details about this. So there is the quantum approximate optimization algorithm and variational quantum eigensolver and quantum annealing. And these two algorithms, like the quantum approximate and the variational VTE, variation quantum eigensolver, they have a lot of variants. But yeah, it's mostly used for optimization problems, so we won't discuss them. Then there is the quantum kernels. There is like involved like quantum supervector machines, quantum clustering, and quantum autoencoders. I will explain like the quantum kernel, quantum supervector machines, and quantum autoencoders. Then we have the quantum neural networks, and we have like different variation of those. We have the quantum convolutional, and we have the convolutional. We have the quantum recurrent neural network, quantum generative adversarial networks, quantum graph neural networks, and a lot. Then yeah, most of the time we are using this parameterized quantum circuits as like the main core of most of those algorithms. Yeah, and I will start with something very simple, which is like, I would say, in classical, it was the first model, quantum perceptron, and in quantum, it's the same. Even like, yeah, the first model, I think in 2001, it was quantum perceptron, so I will start with that. So quantum perceptron is a quantum version of, I would say, or just like the analog, the quantum analog of the classical perceptron model. And it's designed to use quantum gates and circuit to perform binary classification tasks. It depends. Sometimes we can use it even for multi-classification. And it extends like the capabilities of the classical perceptron by incorporating like quantum principles, offering some potential improvements in speed and accuracy. But yeah, it's not proven yet. On the left side, we have like a schematic representation showing using the quantum gates here, like a set of quantum gates of like unitary one, U theta, to manipulate the inputs qubit. Then this is apply a unitary transformation to encode data, as I explained. Then yeah, we have those qubits first are initially in the zero state, are transformed using these gates, which are parameterized to learn the classification boundaries. Then we have some additional Anstrela qubits. Sometimes it helps us with like the processing and measurement stages. On the right side, sorry, it's kind of like an illustration of a very specific implementation of quantum perceptron circuits. It was the first one, the first practical that like from 2019. And it's the same. So the circuit consists of layers of quantum gates applied to input qubits. Then we have here Hadamard, Z gates, X gates, C0, which is C0. They transform the input state through various stages. Then we have some parameters, W1, W2. They represent like the weights that the circuit adjusts during the training and optimize the classification task. Then, as I explained, measurements at the end of the circuit provides like the output, which can be interpreted as the predicted class label. Yeah, but most of the time, this is like a very general implementation. Most of the time, we use some very specific, and we add like some other algorithms or remove layers. For example, this is like what we call like customized architecture. So the main thing is like a perceptron, but we do some, make it like very specific to our case. So this is just an example. So here, we added also Grover algorithm. So this is, the first one is like we have the data encoding, we have ansatz, and that's it. This represents a quantum perceptron. But in this customized architecture, we integrated quantum Grover algorithm to improve the classification accuracy. And here, for example, we have only 2 qubits, and we use like amplitude encoding for 4 features. Then we have an ansatz, we apply like unitary gates, and this is the expressor. Yeah, then it has, as you see here, it has like 3 parameters, theta, phi, and lambda. Then we have the Grover algorithm. So first of all, Grover algorithm is like a quantum search algorithm. It's not QML, but this is like one of the quantum algorithms that are already proven to have like some advantage, and it provides like a quadratic speed up for unstructured search problems. And usually it operates by amplifying the amplitude of the desired solution state, thereby increasing the probability of measuring the correct output. Yeah, in this model, the key innovation is like integrating Grover algorithm for amplitude amplification. So somehow this will speed up the learning process and enhance the probability of the correct output state. And as you see here, so the Grover operator is applied after the initial ansatz, which is the parameterized circuit, which make it like overall, this is our PQC, parameterized quantum circuit. And this operator includes like an oracle that marks the desired state, and a diffusion operator that amplifies its amplitude. And combining this operation, we ensure that the correct output state becomes more prominent in improving the classification accuracy. Then we have the measurement and the classical optimization. So here with this post-Grover amplification, we measure the quantum states and use the results in a classical optimization loop to update the parameters iteratively. Yeah. So this is just like an example. Usually you start with something very basic, even for like right now, for the hackathon, you would start like with a very simple architecture, but you might need to adjust it and try to change a lot of things. That's why sometimes you came up with like a novel architecture. That's here, for example. So this model was slow and the accuracy wasn't good. Okay, what to do? I need to think about something. So yeah, let me try. So make it like as we have a structured search, and we need to find the best hyperparameters to make the conversions faster. That's why we use Grover. Some of this ideas just came like that. yeah, moving to other models. So this is the quantum kernels. This is not really a model, but usually it can be used with other models or used in the models itself. So in classical machine learning, I'm not sure if yesterday they covered the kernels, but kernels are powerful tools used in methods like SVM, supervector machines, and clustering. So the core idea here is to map data into a higher dimensional feature space where the patterns becomes like more easily separable. The quantum kernel extends this concept by embedding data into a quantum feature space. We just like add the quantum word, which called also in our case the Hilbert space. That's like the Bloch sphere one that I explained in the beginning. And here we use the parameterized quantum circuits. So in this space, the similarity between two inputs is captured by the inner product of the quantum state. And probably James, I think, explained the inner products in linear algebra in the first day. So this approach allows us to construct a quantum kernel matrix, which can then be used in classical algorithms like SVM or sometimes in clustering, but now leveraging a representation that could be maybe exponentially richer than classical mappings. And on the diagram here, you can see that the upper part shows the classical kernel pipeline, where the data is mapped to a classical feature space, and the similarity is computed with a kernel function. And there is different one in classical. And the lower part here in the figure, it shows the quantum kernel pipeline where the data is encoded into quantum states, and their overlaps define the kernel values. And this is especially useful in tasks like especially for quantum clustering, where the clusters corresponds like to high density regions in the Hilbert space, and by I would say working in quantum feature space, we can reveal the structures that are inaccessible to purely classical methods. Now that we understand a little bit like how kernels define the similarity between the data points, I would say let's see how this is applied in supervector machine. So yeah, especially quantum supervector machine. So quantum supervector machine is like very similar to any QML model. It used like quantum mechanics to enhance the classical supervector machine. It started like this, but sometimes it's not. But yeah, the key points, like we have the same encoding, but yeah, it's slightly different that the quantum circuit processing. So here the encoded state undergoes like some transformations via a sequence of gates. For example, here we have like G1, G2, and G3, G4. And this processing step is crucial for implementing the QSVM algorithm. Then we have the measurement, and finally, the output is measured to determine the classification results. The measurement operator here, as you see, like I put the equation, is represented with like sigma z is like the poly z matrix, and g theta is the unitary operator. Usually there is like something we call the kernel trick in QSVM or like even in classical. So it's the same as the classical. So here the QSVM, as I explained, it used the kernel function to transform the data into a higher dimensional space where it is easier to perform the separation. And yeah, however, this quantum kernel used the quantum states for potentially exponential speed up in finding the optimal hyperplanes. And this is how we use this quantum kernel that I explained in the quantum supervector machines. And yeah, sometimes, like as I mentioned, there is like different architecture. This is like the very basic. Then there is some, for example, some customized one. So we just like keep changing, adding some layers. This is, for example, here we have just like two operators, and we try to compute the similarities between these two functions. Like, for example, it used the Engel embedding template, and with the swap test, reduce the number of required qubits by half. So here, this is how we are representing the kernel, and it measures like the similarity between two data points in a high dimensional features space, allowance for effective classification. Then here we have a quantum variation on super vector machine with because we are using, instead of the kernel, we are using the strongly entangling layers, and sometimes we combine these two and we have another customized architecture of QSVM. This is just, I'm giving you some examples, but yeah, this is how sometimes you came up with some architecture. But yeah, they must whatever you do, it must be solving some problems. Now moving to another model, which is most of the time we use those quantum neural networks. It's the same as what I explained. There is no difference, slightly differences, but so here, I would say the functionality is the same to any other quantum machine learning model, but yet they offer the flexibility in how they are constructed and applied. And there is a lot of architectures ranging from the predefined models to fully customized or hybrid approaches. For you, probably you will start with the pre-built one. For example, you use strongly entangling layers for your QNN, and there is some tutorials on PNLA. I will share that later on. How to construct a torch layer, or how to transform a Q node, which is this circuit, into a torch layer, and technically your quantum neural network. So for example, here, this architecture employs Ingelin coding, which is we discussed this earlier as part of its design. Then, yeah, the choice of each component within a QNN, it's depends heavily on the nature of the task and the data itself. So it's very not random, but not that straightforward. And I will explain that in details when I discuss the challenges. So in quantum, we cannot generalize. So this is okay for how we have a data set. We can use Ingelin coding, and we can use this, for example, this architecture, and we will get for the accuracy 90%. Okay, let's change the data set. So this is a model, it is good, it gets 90, or I will make it 95%. Let's change the data set. Okay, I will keep the same model. The model is good, so I change the data set. Then what? The accuracy is random guess is 50%. So sometimes you need to adapt. So you keep not playing, but you need to know. Sometimes you don't need to know. But right now there is something called quantum architecture search, and I will try to cover that later on. But yeah, QNNs is the same as any other models. It's just how you structure your model is slightly different. Another model is quantum graph neural network. So here it's slightly different because so it depends. Sometimes on those names, for example, we take the existing graph neural network, classical. So we put quantum. It does a lot of meaning. I would say every research group take it how to make it quantum. So they start thinking which part can be replaced by a quantum circuit. Okay, so here in this case, we keep the same as classical. We have some topological data analysis to represent the classical data that we have into graphs, and from those graphs we embed them as quantum state. Then we use variation quantum classifier. Then we have some average polling, and here, as I mentioned, sometimes you add classical layers. So it's an hybrid approach that has the graph parts, but also it's it involves there is for example, this VQC is the same as QNN. Yeah, but I won't go into the details of this one. Then we have another model, which is, I would say, the same. They work the same, but yeah, this is quantum convolutional neural networks. So the classical convolutional neural networks are built upon convolutional layers for extracting the features of the input and are established architecture for image classification tasks, for example, especially in the computer vision domains. So here the quantum convolution neural network extends the fundamental properties of these classical CNNs into the quantum domains. Its structure consists of applying alternative convolutional layers, polling layers, and fully connected layers. Then this convolution operation are performed as parameterized unitary rotation, which is like PQC and SAT. Then the pooling layers are used for dimensionality reduction, but since in quantum systems it's not possible to directly remove qubits from the circuit, they are implemented by measuring a subset of the qubit and use those measurements to control the following operation. So yeah, just like whenever you start with the classical and make sure like which part like can be replaced by the quantum, then you start doing that transformation. I'm not sure about the timing. Is like I'm good or like because like I still have a couple of slides.
لا لسه مفيش مشكلة معنا وقت.
Okay. Yeah. So then there is this quan. So to be honest, like it's very similar and sometimes it's confusing. So this is like convolutional neural network. So this is different from the previous architecture, but the idea is to have a convolutional layer where instead of processing the entire input data with a global function, we will put it as local convolution is applied. Here, only the convolutional layers are implemented with the parameterized quantum circuits. So this convolutional neural networks introduce preliminary layers before the classical CNN to manipulate the inputs. That is like pre-processing using one or more quantum layers. It's like the opposite. Then the input of the first classical layers is a quantum output measured classically that preserves maybe a large amount of information for improving the contextual feature extraction in the classical layers. Then in the current quantum hardware systems, usually we have the limitations on the number of qubits. So this architecture represents a valid solution that somehow fixes the problem. Since low qubit circuits are sufficient to perform some required tasks, while the deeper circuits are still implemented with the classical computer. Then here we have another model, which is quantum ResNet. So this is an hybrid extension of the classical ResNet architecture. So in the top part of the figure, here we see the classical ResNet pipeline. So we have some car images are passed through our ResNet 34 backbone, then followed by a series of fully connected layers. This is just classical. Then these layers progressively reduce the feature dimensions, eventually outputting the prediction of the car models, such as like Audi and other models. And then this is the standard deep learning approach for image classification. Then we have the quantum part. So in the bottom, so this is an hybrid quantum classical ResNet. So the process begins with the same way. We have that ResNet 34 backbone to extract like the initial features. However, instead of passing these features entirely to the classical fully connected layers, some of them are mapped into a quantum layer. Then this quantum layer is built from parameterized quantum circuits. In this example, we are using Hadamard gates and like to prepare the qubits, followed by some rotations, Y, Z, and X that are parameterized by trainable weight. Then we have the measurements from this qubit provide the output that are then passed back into the network. Then the quantum layer can be repeated multiple times, enabling deeper hybrid structure, which we call like expressibility. Finally, the like quantum classical features are sent into the last fully connected layer, which produce the car model prediction. I would say the key advantage, or like the potential key advantage, is that in this hybrid design is that like it allows us to combine the power of classical feature structures with the expressive capacity of these quantum layers. So the quantum layer can capture the correlation and high dimensional features mapping that might be challenging for purely classical layers, and somehow potentially improving the classification accuracy or any performance metrics. So in short, like this quantum resonance, it skips the backbone of the classical resonance, but it inserts like a quantum layers into the pipeline, making like promising architecture for image recognition tasks under the hybrid quantum classical settings. Then yeah, we still have a couple of models, but as you saw, it's like it's like the same functionality, just like slight changes. And this changes comes from the classical. This is another model, and this is quantum recurrent neural network. So this is inspired also by the classical RNNs that use the sequential data to solve temporal problems. Especially we are talking like especially for classification task for time series or predictions. So in this quantum recurrent neural network, we have the RNN layers are replaced by like a very specific type of parameterized quantum circuit. It's called like the quantum, I would say, recurrent neural networks cells. So instead of being dense like the other PQC, parameterized quantum circuit, this QRNN, like the cells are highly structured circuits with fewer parameters that
نويلة
are.
معلش
Yes, please.
معلش كان في سؤال بس على الجزء اللي فات فكان قاعد
Yes.
مستني ياخد فرصة أو مستنية تاخد فرصة. معلش خليها تسأل بس الأول.
Okay, my question here is that the first question is that I can use like two models together. For example, like QNN with another model. And the second question is that how the quantum really deal with the correlation. And you can tell us more in details for that point?
Yeah. Sure. So the first one, it's not like you can combine them. You just, because if you combine two models, it depends. So maybe one of the tasks, for example, I mentioned that for this quant, it can be used to extract the features. Okay, this is done using the features. Then I can use another model to do the classification. This is an example of combining two models. The other example is like instead of exactly the two models, you can just take the architecture. So for example, the one that I give, so you have like a quantum perceptron, you just take the idea of global algorithm and you integrate it with that. So it's kind of like not you take like the full algorithm or the full model, you just get like the concept or like a part of it. I hope that answered your question. Regarding the second one, yeah, so this is a kind of like a fundamental one, how the correlation exactly contributes in QML models, or how is it like the superposition. So there is a lot of studies they try to do that. For example, I will try to control this entanglement, or maybe because like there is two things. So the correlation, sometimes it means the entanglement. If we want to make two qubits correlated, so I will apply like entanglement, which is like CNOT gates. And the correlation, I'm not sure which one you meant, like the correlation in the features itself. Sometimes correlation in the features is like just they are correlated, means they rely on each other. Sometimes like we have a label and this is very correlated with a feature, so it means like it affects. If we don't know anything about this feature, of if we remove it, it will be very hard to like find the decision or like predict the label. That's like the correlation in the data, and there is the correlation in the QML, which is like the entanglement. So the data, I think I just explained. I will explain again for the QML. So exactly how does it help? I cannot tell you exactly, because like there is some papers, they do the analysis, like deep analysis, like, okay, I will try to have like a circuit with more entanglement and see how that improve like the accuracy or a very specific model, or sorry, a very specific evaluation metrics. But as I mentioned, it's like it involves a lot of factors. So even if we try to control everything, we have the data encoding is contributing, optimization is contributing, that PQC is contributing. So if we want like solely try like to have exactly what is the role of entanglement, or it's not the role, but it's kind of like what is the effect of entanglement in a quantum machine learning model, exactly, I don't know, like, to be honest. But yeah, I can share a couple of papers. I think I have some of them. We try like to understand the behavior of like, or what is the effect. But yeah, it's always like involves a lot of factors, because like you cannot just remove all the other stuff. Even if you fix it, still like there is some randomness, and quantum is like has the probabilistic nature, so you cannot generalize or say, okay, this is happening because of this.
Okay, so I can't use the correlation thing for the classical and the quantum, both of them, or it just separate the correlation for the quantum and the classical as well.
So yeah, so I'm not sure what do you mean by classical and quantum. So correlation, as I mentioned, so correlation is like in classical, it doesn't mean that it's not a concept. This is like purely for quantum. If we are talking about
I mean
quantum,
for selecting the features.
okay,
I mean
sorry.
for selecting the features.
Okay. Then yeah, for that part, it doesn't matter. So yeah, you do it like this is a very, I would say, general in data, or like the pre-processing part. So once you start, you have a data, you need to study the features. You cannot like just, okay, I will use the all features. No, you do there is the confusion matrix, the correlation matrix. I'm not sure if I have, but at the end I can look into some examples and show you, or maybe like with Walid can, like during the lab, he can have some figures of the correlation of the data. So this correlation maps, or like a matrix, it gives you like how the features are correlated with each other. So it doesn't give you something extra, it just show you how to use the features, or how if I want to remove or reduce the number of features, I need to understand which one to remove. So I will reduce or remove the less correlated one, because like they affects each other. So for example, or especially for the label. And I think if I don't have a figure now, but with the figure, it will be very clear for you. Yeah. But yeah, at the end, I can, I can show a figure of
I
like
guess I've worked before.
Sorry,
I saw the figure, so I get this point. I have
Okay.
worked before in this model.
Oh, okay. So that's the correlation part.
Okay,
yeah.
thank you.
Welcome. Yeah, so I'm not sure if I explained the quantum recurrent neural network or not yet. I think I just started, right?
Yeah, I got it. Thank you.
Welcome. Yeah, so I was explaining this quantum recurrent neural network. So I think I did like a, so yeah, usually, but yeah, the main issue in this architecture or this model is the coherence. But it can be mitigated by some implementing multiple quantum recurrent neural network cells in a very different way, because like like this recurrent, it means like we make it like rely on or take the memory of the previous layer. So here in quantum, we have the decoherence, and decoherence is like one of the fundamental problems when the qubit lose its quantum properties. So they are not qubit anymore. And this is like a very short time. We are talking about nanoseconds. That's why sometimes like using a recurrent neural network can be very challenging. Then yeah, moving to another model. This is before the last model.
Excuse me.
Yes.
Yeah. I have some question
Yeah, sure.
about the classical layers and inside the neural network.
Yeah.
How does it work after embedding data into a quantum states? Actually, my question is how could classically or how can we classically manipulate a quantum data and how to switch between classical layers and quantum layers and manipulate the same quantum data?
Okay, this is a good question. So technically, from the coding aspects, it's kind of like easier, especially for me, like using Tenelane. So there is a transformation of that Q node into a torch layer. So your circuit will be, okay, for example, I have a classical layer, then I have a quantum circuit. This quantum circuit, of course, like how to integrate it is like very challenging. That's why there is like some libraries, they switch this quantum circuit in a Q node, which is like a torch layer, and you put it like that. Then you combine it. This is from the coding aspect, it's kind of easier. How it works, usually, as I mentioned, so once you do the measurement, you get like some outputs, and they are classical outputs, probabilities. And you add some, like I would say, some not activation function. Technically, it's activation functions like ReLU or sign or any other functions. You make it like to be suitable for this classical layers to make the decision if it is at the end. But yeah, without classical layers, especially when we are dealing with multi-class, we cannot use only the quantum, even if it is in the beginning. For example, this is a scenario. We have a data, we do the pre-processing, and we did like the data encoding. We are using, for example, QNNs. We have a parameterized circuits. Everything is good. We do measurements. And yeah, this data has like, for example, 5 or 10 classes. Okay, we have everything. Then yeah, at the end, we will get some probabilities, and this is the classical output. We cannot just base it on those classical output to do the prediction. So that's we need some classical layers. How is it connected? It's very simple. You just like, as I mentioned, you use some classical, I would say, activation function or like functions. Then you you connect that, then you get your output. But yeah, from the coding aspect, it's kind of easier. You just like convert whatever you are trying to do with your circuits in a Q node, a torch layer. Then you have a class. So for the example, some linear classical neurons, then you have some pooling, whatever, like very simple to the quantum, to the classical. Just instead of having, for example, a convolutional layer, we can put that torch layer Q node, which represents the quantum circuit, and the integration is smoothly.
Okay, definitely. But does it broke the mathematical formalism or dynamics between the classical and the quantum layers?
Somehow it does, but like we are trying. That's why like they think about like why we need this, or maybe sometimes we do the ablation study to see how does affect like okay, there is always in quantum or even in classical, there is always a trade-off. So for example, if I am breaking this, I would say this loop from the classical into quantum, or I'm mixing all this stuff, of course, like I'm improving the accuracy, but I'm also changing something. If it is not, the accuracy is already decreasing, and for example, the computational resources are getting better. But yeah, it's not like a general rule, or like there is like a general facts. You need to explore and see what exactly is like happening, or what is the effect on that.
Okay, thank you for explanation or clarification. Thank you.
Welcome. Yeah. This is quantum generative adversarial networks. So classical GANs have a generator that generates new fake data and a discriminator that distinguishes fake from real data. However, this type of architecture is too large to be implemented fully in quantum. It's like right now, I don't think there is, unless some recent papers manage to do that. So it's possible to design hybrid QGANs where either we use the generator or the discriminator is implemented in classical computing. We cannot use both, but sometimes, most of the time, we use the generator quantum and the discriminator is like classical. And that's also try some, we try to make it like as a classical or not, embed this quantum layer into the classical architecture. And this is what we see in this figure. So the generator here can be divided into multiple sub-generator blocks, and each of them responsible of generating a patch of the full image. Then at the end is like the generated images is found by concatenating like the patches. This is good for images, for generating images or reconstructing. Sometimes we use it also for denoising images. If we have an image that has some noise, we can use it to denoise it. Same for the quantum autoencoders. So classical autoencoders are models composed of like an encoder that performs the compression and a decoder that performs the decompression. In a very similar way, quantum autoencoders reduce the dimensionality of quantum states in order to encode the information into a smaller amount of qubits than besides being applied for transforming and mapping large problems into a smaller quantum circuit. These quantum encoders are also applied for denoising and sometimes maybe for, I would say, anomaly detection, since they extract like features from the initial quantum state, neglecting the noise. And by this, I end like the part of like the models. This is important. I will go into the challenges. So quantum machine learning, as I explained, is a promising field. It's nice, but there is a lot of several key challenges. It's like classical, even classical machine learning is started like in 1956, I think, or something like that. So, but yeah, this is, as I mentioned, it's only in 2015 and 2017 exactly with like a paper in Nature. So there is a lot of challenges that we need to address before we can achieve the practical impact. So the first part is the data encoding. So one of the first bottleneck is how we encode the classical data in quantum state. So many of the encoding methods are, as I explained, are inefficient, or sometimes it requires like a large number of qubits or some complex gate. So this makes them difficult to scale. If we are talking about like using a full data set or full features, full number of features of the data, it's very hard. And sometimes, moreover, during the encoding process, there can be some loss of data fidelity, meaning that the quantum representation might not preserve all the important information from the classical input. And this reduces the effectiveness of the downstream learning task. And another thing is like we cannot make sure that, okay, this is very efficient. No, like sometimes because like you encode and you just base it on the performance, like you just at the end, and that's at the end there is a lot of factors involved. So this is like, it's the same with the entanglement. We cannot say, okay, maybe this encoding is better than this, but like we need to make sure that, okay, it's better, but still like some unknown factors are involved that we cannot control. And another challenge is the algorithmic barriers. So even once the data is encoded, everything is good, we solve that problem, the algorithms themselves face issues, and one of the most widely discussed problems is the barren plateau phenomenon. So the barren plateau is like where the gradients vanish as circuits become steeper, as you see here in the figure. It's making like the optimization nearly impossible. And the scalability is also limited because most of like current algorithms only work well for small systems. And finally, we have the hybrid integration between the classical and the quantum component is then not seamless. Like as you mentioned, like your question is like valid because like we still or like we need better solution and frameworks that can efficiently combine the two, like the classical and the quantum. Then another challenge, which is the benchmark. This is very important. Right now, there is a lack of standardized benchmark and the metrics in QML. So this makes it like very hard to compare different approaches fairly. And furthermore, the notion of like quantum advantage, right now everyone is talking about achieving quantum advantage, but especially in machine learning or quantum machine learning, is still not clearly defined. So without a clear benchmarks, it's difficult to demonstrate when a quantum algorithm truly outperforms classical methods. Even in that, like this comparison, we need to make it fair. So we need to make it like very, I would say, very similar to the model that we are trying to compare, same number of parameters, same number of layers. Okay, then we can say, okay, this is better than this. Then another challenge, which is the noise and robustness. This is more into the hardware effect. So the quantum devices today are inherently like noisy, most of them. So QML models are very sensitive to this noise, which can be completely degrade the performance. But there is some error mitigation strategies exist, but they are often inadequate or too resource intensive. So developing algorithms that are naturally robust to noise is therefore a critical research direction. And most of the times that's like having access to the hardware, it's not that easy. Sometimes you don't have to, you cannot test on the hardware. So there is the noise modeling. So there is some using cross operator. You can model the noise. There is the implicit damping and other 5 noise models. I can share also some resources regarding that. You just model them in the simulator and study the noise and robustness of your model. Then we have the circuit design. So I also mentioned that. So that parameterized circuit sometimes is like just like a black box. So designing effective quantum circuits is another hurdle. So currently much of this is manually architecture design. We start like with some pre-built and then we keep changing this case, add this gate, do this, but it's not scalable. So in the search space for good circuit structure grows exponentially with the number of qubits. Every time we increase the number of qubits, we have like multiple options to design this, and which make like this systematic exploration very challenging. And moreover, like many circuits suffer from the inefficient gate or some redundancy, like just like we add like multiple same gates and it doesn't help with anything. And there is no widely adopted method for systematic optimization of circuit structure yet. But yeah, this is another field. It's called like the quantum architecture search. There is some automatic techniques. You can just design your own circuit instead of trying to do it like manually. You just define a space and try to do some genetic algorithms or like reinforcement learning to design automatically the best parameterized quantum circuit, or like what we call like ansatz for your model. Then the last one is the hardware. So this is like the practical limitation of the hardware. So quantum computers still have like severe qubit constraints with only a limited number of usable qubits available. So even now, I think with IBM, we have access to the 264, I think.
But it's not really free.
Yeah, it's only 10 minutes per month. So I know that it's not that good, but yeah. And the top of that, the short coherence that I mentioned, time of qubits, means that we can only perform a limited number of operations before the quantum state decays. And we are talking about nanoseconds, but this is more into the hardware part. They are trying to increase that, and sometimes like also the fidelity of those qubits. And yeah, these issues restrict the size and the complexity of QML models that can realistically be implemented on current devices. And of course, like we are talking right now, everyone is looking forward like for the full range devices that are like perfect qubits, but it's still time for that, I think. But yeah, most of the hardware companies are trying to do that, especially sometimes like with topological qubits. So there is like, I won't cover this, but like there is like different qubit technologies. There is this supraconducting one. There is like topological. There is the photons one. It different like from different companies. But yeah, I don't know much about the details because it's more related to the hardware part. So overall, while like quantum machine learning showed this great promise, progress requires also overcoming this and these challenges, from data encoding and circuit design to algorithmic optimization, benchmarking, robustness, and hardware limitations. Then I will move, I think, maybe to the last one. Yeah, still time, right?
يعني فاضل ممكن دقيقتين بقى، ناخد دقيقتين اكسترا او حاجة، بس هو الوقت خلص.
Okay, then I will just like do this briefly. So in quantum machine learning, there is like a lot of potential application across many different fields. There is the cybersecurity. We can use the like malware detection, user authentications by learning complex data patterns. Then there is also we can come up with some different strategies for QML against cyber attacks. Then in healthcare sector, we can use it like for medical image analysis, like detecting tumors or abnormalities in radiology scans. Then in material science, it's more like to drug discovery or some prediction of the properties of the materials. Then in climate modeling, we can use it like to handle the enormous data sets and highly nonlinear system is involved. And sometimes it can improve the ability to predict extreme weather events or model the global climate dynamics with higher fidelity. Then we have the finance. In this, we have like the fraud detection, market prediction, risk management, and other application, credit scoring. And for the optimization, this is like strictly speaking, optimization is not a domain like healthcare or finance. It's like cross-cutting tool. Sometimes like we use a couple of techniques, but it has their own technique, quantum optimization part. Then yeah, I had a couple of slides, but yeah, I can just like skip to the end. And yeah. So yeah, thank you for your attention.
شكرا يا دكتورة، يعني أرجو إن بقى تكونوا استمتعتوا بالسيشن دي زي كده بالظبط. لو في حد عايز يسأل اتفضل على طول.
Okay, thanks for this presentation. It was really good, and I hope we have like more session from you in the future.
Thank you. Yeah, definitely. Like, this is my email. If you are interested, just like to know more about any of those concepts, or even like you are just interested in something, we can have like a discussion. Yeah, just send me an email, then we can discuss later. And of course, like I will try. Like I still didn't make like I'm planning to make like a very detailed resources list of resources that can help you, especially like for the hackathon, how to design the model and all of those, especially some tutorials with like I would say it's like you start with those, then you try to adapt your architecture and your model based on the problem that you are targeting. Hopefully I will try to prepare them and share them by tomorrow, but yeah, definitely before the hackathon.
All right, I will send you an email maybe tonight, and hopefully we'll wait for your reply.
Yeah, sure, just send. I might take a couple of days based on if I am busy, but I will definitely reply.
Okay, thank you.
Welcome.
ممتاز جدا، ألف شكر يا دكتورة نهيلة، الصراحة محاضرة جميلة جدا وأنا استمتعت، والشباب يعني الإيموجيز بتاعتهم بقت تبين إن هم استمتعوا جدا. فبإذن الله بقى يعني هناخد بريك دلوقتي نص ساعة، ونرجع تاني الساعة 8 بالظبط مع دكتور وليد في اللاب. وما تنسوش بقى يعني دكتورة نهيلة هتبقى معانا في الهاكاثون، فبإذن الله هيجي منكم. يعني هتبقى صحبة كويسة، ويعني أتمنى إن إحنا نستمتع جميعا بالهاكاثون الجميل ده اللي هيكون في سبتمبر. دلوقتي نروح بقى للبريك، وهستناك في الساعة 8 بالظبط. شكرا دكتورة نهيلة.
Thank you. Yeah.
جاهزين؟ طيب ندى بس اللي جاهزة كده مش هنبدأ. دكتورة سليم معانا، طب ماشي. فين باقي الطلبة؟
جاهزين.
طيب أظن بقى مفيش وقت نستنى أكتر من كده، خلاص استنينا 5 دقايق وده وقت كافي. هنبدأ بقى اللاب. يا ريت تكون المحاضرة بقى كانت عاجباكوا وتحمستوا أكتر تشوفوا ده براكتيكال هيبقى عامل إزاي. معانا دكتور وليد، PhD ريسيرشر برضو. أنا هسيبه يعرف عن نفسه كالعادة يعني عشان مش هقدر أكفي. معانا برضو باشمهندس عبد الرحمن من امبارح، هيبقى الكوتشير بقى في اللاب. منور يا باشمهندس وليد، اتفضل.
السلام عليكم، كيف الحال؟ Yeah,
وعليكم السلام،
so
منور النهارده.
thank you for the introduction. Yeah, so just introduce myself quickly. I'm Walid. I just got my PhD in quantum machine learning in Morocco and currently a postdoc researcher in Ibrahim Lab in the NYU University at the Cybersecurity Center. Yeah, and happy to be with you here, guys, and just teach you about the practical way of quantum machine learning. I guess you felt overwhelmed with the Nouhaila presentation. Yeah, as you know, there is a lot of quantum machine learning models, a lot of varieties of quantum machine learning. So don't be afraid. It's a long way. So yeah, for this session, I will try to make it a little bit light as it's I like try to make it as simple as possible so you can implement quantum machine learning yourself. And of course, I provided you with some resources that can help you throughout the week before meeting in the hackathon. Right. Yeah. So I will proceed by sharing my screen. Let me check. I need to authorize it. So do you see my screen? Does my screen is visible to you guys?
واضحة جدا، اتفضل.
Okay, great. Yeah, so today's session will be a lab walk through step by step how to implement quantum machine learning, a sample quantum machine learning model, which is the usual variation quantum circuits, and I'd show you how it can become a classifier. Yeah, so first of all, what we do here, I'm going to implement this quantum machine learning using the Penny Lane platform. So as you
وليد
maybe
معلش.
Nouhaila. Mm-hmm.
لو ينفع بس تزوم ان شوية.
Yeah, sure. Is it okay now?
تمام افضل.
Awesome. Yeah, so as I mentioned, I'm using the Penny Lane library here. So there are a lot of libraries to run quantum or quantum circuits in general. Probably Nouhaila mentioned some of them. There is Qiskit, there is Q#, there is a lot of languages or libraries, quantum libraries that help you simulate quantum circuits and also run them on the quantum hardware itself. For this lab, we will be using PennyLane library, which is made by Xanadu company. And yeah, so first of all, what you are going to do is you need to install PennyLane. I'm using Google Colab, so I will be sharing with you this notebook for later, so you can practice it yourself. And also, I'm adding some tasks for you in order to cement these kind of concepts and help you understand more these concepts of quantum machine learning. Also, we will need the MATLAB for visualization and Scikit for loading data sets. So as you know, currently I will be using only classical data sets for simplicity. Let's move into the second cell. So first of all, we need to import PennyLane and also import a quantum machine learning model from PennyLane in order to help with it, every quantum machine learning functionality brought to us from PennyLane. Also, I need to import NumPy. As you can see, I didn't use the NumPy directly. I took it from PennyLane. In order to do that, because if I did import it directly from NumPy, the parameter will not be updated from using the PennyLane framework. So PennyLane make it twisted the NumPy functions in order to make the parameters updatable and differentiable throughout the PennyLane framework. Also, for this first example, just to mention, I am using two examples here. The first example is the Make Moon dataset, which only has two features. This is a sample example. The another example is the MNIST dataset. So this one has also, so it has a large set of features. Yeah, so I will walk you through how we can do the classification for both datasets and how we can tweak the parameters in order to make the model more efficient. Yeah, so this is the Moon dataset. As you can see, this is not linearly separable. We are going to use quantum circuits in order to classify these datasets, make the best possible parameters for the quantum in order to make this nonlinear classification possible using the quantum model. As you see, we have two features that describe the dataset, X0 and X1. I believe Nouhaila mentioned to you that we first of all, we pre-process the dataset. So for this type of dataset, we don't do much for the pre-processing part. We only load the dataset and split the dataset into two data for testing and training the model. We take the test size for 40% of the dataset to be the test, and for the training dataset, we take 60% of the dataset. So from these 200 samples. All right, so after pre-processing the dataset, we need to encode this dataset into the quantum circuits. Beforehand, we need to define the quantum circuit first using a quantum node. So this is the quantum node in PennyLane. This is a wrapper that turns Python function into a callable quantum circuit. So you can differentiate this quantum circuit, at least using simulation. Yeah, in this example, so we are going to use two qubits, and we define the simulator, which is in the quantum machine. In PennyLane, we have this simulator that simulates quantum circuits called default.qubits. and this is the device, and we define how many qubits we want in our quantum circuits. And the shots is how many measurements we want to do in this example. So as you can mention, there is two lines here. The first one, if you uncomment it, so the first one, I'm setting the shots to be none. This means that the quantum device or penny lane try to simulate the quantum circuit in an analytical way. This means that the quantum circuit will be only simulated using multiplication of matrices, and we are not using the probability side of the quantum circuit. So this one is only made for like debugging stuff and know where you use your problem in your code. So in realistic problems or realistic cases, we don't use this part. We use the second one where we define how many shots we want or how many measurements we want. Because for each measurement, we have a probability of errors. So we need a lot of measurement in order to reduce or average out this error in order to make our computation more reliable. So this is called the noise mode. And the first one for debugging stuff and know where you have the problems in your code, but not specifically for the quantum per se, because it is not quantum actually. This is only a simulation for exact simulation, so to say. Yeah. Finally, after like defining the device and the quantum simulator, we need to create our quantum circuits. So this is the model or the function that will help us create the quantum circuit or the quantum model. So what does the quantum model contain? Quantum model contains, first of all, the encoding parts. So this is the feature map encoding, where we map these quantum or these classical features, so the feature x0 and x1, into circuit rotations, which means, for instance, if you have x0 is, for instance, like let's say has a value of 1 or 1.5, this means we need to rotate our first qubit with 1.5 degrees. As an example. For the second one, if we have the first feature, the second feature of our sample to be 2, we rotate the second qubit with a rotation around the y axis with 2 degrees. So finally, we do a C0, which is an entanglement between the two qubits. This one's mention which qubit you want to apply this rotation on. I believe you know what is the next step now after encoding. Will somebody tell me? Okay, let's have some time. I would say we need a variational quantum circuit or a parameterized quantum circuit, meaning that we need a trainable quantum circuit in order to make the model learnable. What we do, we apply some rotation on the quantum circuits or rotation on our qubits. These parameters, this rotation are the parameters. As you see, the first qubit get a rotation that do multiple rotations. So the first parameter will be do rotation around the y, the x-axis. The second parameters or second rotation will, let's make it sample. So excuse me, I will repeat that. For rotation, so we first apply a rotation around the x-axis, then we follow up with y-axis rotation, then we follow up with z-axis rotation. So this is done on the first qubit. We do the same for the second qubit. So these parameters are different. As you can see, they are mentioned 0, 1, 2, 3, 4, 5. You can add as many as you want based on your parameterized or variational block. So let's make it for you clear before moving. I will be mentioning this variational block as an ansatz. So we'll be mentioning it interchangeably with ansatz or parameterized quantum circuits or variational quantum circuits. They are the same, referring the same thing for the block, for the trainable block. Then we apply a CNOT gate in order to correlate between our qubits and help the quantum model learn more patterns from our data sets. Yeah, so as you see, I applied only one layer. You can apply as many as you want. Just copy paste this part, and then you will have a second layer applied. And you can go for third layer, the fourth layer, depends how complex you want your model to be. So this problem of the two-bone example is a binary classification problem. So which means whether you have 0 or 1. Since one qubit can give us a probability of to be 0 or 1, we need to measure only the first qubit. We don't need to measure the third and the second. If you have like a multi-classification problem, then the first qubit will generate two probabilities, 0 and 1, and the second one also will do the same. So we can, for this case, we will have like four features, four classes. So instead of for one classes, two classes, if we measure the first qubit. So as we have a binary example, we only measure the first qubits. So this is the measurement is will go to give us an expectation value within the range of -1 and 1. And to get a meaningful results, we need probabilities. So we take this, so to say, logic from our quantum circuit and feed it into our model wrapper to turn these expectation values from the range -1 to 1 into a range of probabilities from 0 and 1. This helps our model next in order to be trainable. Some cases, the second example I will show you, will use only these largest parts with -1 and 1. For the initialization, we take random quantum circuits. Let me first run the notebook. Load the example here. Then here we defined the quantum device or quantum simulator, quantum model with encoding and variational trainable parameters. Then we transformed the expectation value from expectation values to probabilities. After that, we initialize the quantum circuit. As you know, we need to initialize after the win, before the win the optimization. Right? Okay, so you can also plot your quantum circuits in order to have like an intuitive visualization of your circuit. First, as you see, this is the first layer of encoding. The first rotation will implement or encode the first feature, x0, of our dataset, or of our sample, first sample. The second one do the same with the second feature. We apply the parameterized quantum circuit or the trainable block, where you have this is the trainable parameters. That's our optimizer going to optimize in order to make our this variational quantum classifier trainable and learnable. Finally, we do measurements for the first one. So we either get a probability of getting 0 or 1. So if you get a probability of higher than 0.5, this means that we have the class, so the sample is in class 1. if the probability is less than 0.5, then the class of this sample is 0. We'll skip this one because this will be as hint for you for the tasks I will give you in the end of this lab. Next, we need to define some functions in order to help. So this is, we end up, like, as you can see, first of all, we have the classical part. Then this cell is the quantum part. Then we move into another classical part. The classical part is we define the loss function and the accuracy function in order to help visualize the performance of the model. So for here, we use the binary cross entropy using the prediction from the quantum circuits, this measurement. Then, yeah, we do here, we clip the prediction in order to like avoid this log 0 and to make the computation more reliable. Yeah, so this is the cross entropy loss function. We define it here. After that, we need to define the accuracy, as mentioned to you. If it is higher than 0 or equals 0.5, this is class 1. Lower, this means it is class 0. We use the quantum machine learning from Penny Lane for gradient descent optimizer. So this is a classical optimizer that optimizes the parameters we have in this block. So this will be an iterative problem. So first of all, we define this. We take our first sample, we encode it to get the first parameters. We measure the prediction and feed it into the loss function. The loss function helps with the convergence of the model, the loss and the update of the parameters. And with the update, we update again this rotation and we run the circuit again. And this loop gonna continue until the model converges. So for me, I use step size to be 0.5 for the gradient descent optimizer. Okay, this is for this example, we only use one batch training. We don't need mini batch trainable because it is a sample example. Right, yeah, this is let me run the circuit. Okay. All right. So how much steps or how much iteration I want this optimizer to do it, I need to define these hyperparameters. In my case, I took 50 steps. For you, you can further increase it to 100, but expect the model to take much time. Because in our example, what we are doing, why take that time? For example, for one of you will tell me, okay, so if I run this example using a classical optimizer, then in a second I get the result. Yeah, true. But why you are getting delayed results using the quantum circuit? This is because we are doing quantum simulation, which means that we are trying to simulate. So apart from this optimization part, we also load our program by simulating this circuit. So this circuit is a matrix multiplication. So now this for each gate here, quantum gate, it is a matrix, and if we add more qubits, the matrix gonna grow larger. So this way we only rely on rely on classical hardware to simulate this larger matrix multiplication. I believe that the largest number of qubits that we can simulate is 40 qubits using using supercomputers, classical one. So it is not that much to simulate, which it gives you an intuition how hard to simulate these matrix multiplications. All right, I guess we are in the 20 steps. As you can see, the accuracy bit by bit is increasing, and also the loss function converge. Yeah, this may take another 1 minute. Yeah, I can take some question. Then in this trainability. Some of you have any question? I believe this was clear, right? Or should I explain or elaborate on other parts?
Actually, I have some question.
Mm-hmm.
Okay, go on. Go ahead, Dale.
Okay, so my question here, how to reduce this time, and should we make it steps like the way you did, or just one step, and it takes longer, or it's just the same way?
So yeah, the question is the same: how to reduce the time, right? So to reduce the time, actually, there is some instead of using the default qubits. So this is like the usual or the usual simulator from Penny Lane. There is another, I guess, called Lightning qubit. Yeah, I will be talking about this one in the next slide, next cells. So this one use a better way to do matrix multiplication. So it uses like GPUs in order to simulate the quantum circuit to make it faster. So instead, to answer your question, you can use the Lightning qubit instead of default qubit device for simulation. We're going to discuss this in the next cells and show you how to do it. Does this answer your question?
Okay. So
Yes,
you believe
thank
that?
you.
Okay.
So you believe that manipulating the circuit on or simulating the circuit on a classical simulator will take a lot of time. But if you go and use hardware, quantum hardware, do you believe it will be faster than the simulation or even the classical optimization or a classical machine
Yeah.
learning?
True. Yeah. Yeah. So exactly. Then it will be faster because if you use the quantum hardware, well, you are not simulating it. You are using directly quantum hardware because
Use
you have
okay.
yeah.
Go.
If you have the quantum hardware, so instead of going directly from, could you see me because I'm always speaking with trying to simulate with my hand. Could you see me?
See
Anyway,
what?
so see my video. So I'm just trying to simulate.
No, only we see
Okay.
the notebook.
All right. Yeah. Okay. So instead of going from simulator optimizer to optimize the update, from the quantum hardware to optimizer and update the parameters, so what you are doing is you first simulate this quantum hardware. So this is an extra work. Instead of doing it directly using quantum hardware, using quantum simulator, you're first simulating the quantum hardware or quantum circuit, then going through the optimizer for optimization. And this is done throughout the loop. Loop could be like, as you can see, I'm doing 50 steps. And in case of mini batch, it will take much longer. So yeah, to answer your question, it will be faster than the simulation as you are using directly the quantum hardware instead of simulation.
Okay, that's clear. But there is another side of the question. I'm also asking about this. Is it will be faster? Will it be faster
Okay.
than the classical machine learning?
Mm-hmm.
Because we here using a quantum hardware and another classical optimizer. So the switching between quantum and the classical and the return to the quantum again.
Yeah.
What do you think?
True.
Or
So this is only a simulation, actually, what I'm doing right now. I'm not running it on a quantum hardware. So if you are asking about if we got a large-scale quantum hardware, would it be faster than a classical computer? Right?
classical algorithm on a classical computer, fully classical algorithm.
Yeah, compared to a quantum algorithm,
Yes.
quantum machine learning model.
Yes.
Yeah, so this is a debate field of research, actually. And some of the researchers, or what we are doing, working on, is that we are trying to look for where the quantum hardware could be beneficial for which type of data set. In the majority of cases, they say that, or the quantum machine learning model perform better at quantum data sets. So if you got like a quantum system, so this quantum system, you can only express it as quantum state. So it's directly implementing the quantum state in the quantum hardware. So in a way, the data set speaks the language of the quantum hardware. So if you come up with a classical data set, you are bringing someone that speaks another language of the quantum hardware. So there will be a translation. This is the quantum encoding part. So this is the translation we need, right? Instead, if you have like a quantum circuit, a quantum system, already expressed as a quantum state, you don't need to do a translation. The quantum hardware directly speak to the data set and make it easy for the quantum machine learning to outperform the classical computers. So this is all a matter of translation. This is my way to simplify it. For instance, the classical computers cannot, for sometimes cannot perform well with the quantum dataset because we need a translation of the dataset to the classical one. This is the same with the quantum hardware. Yeah, right. So this is how I can explain to you. To answer your question, whether we're gonna have an advantage, quantum advantage or not, we are still looking because currently we have like a small scale quantum hardware in order to do enough benchmarking between the classical and quantum hardware. At the moment, classical hardware outperforms quantum computer, but once we got enough qubits to do like an exact benchmark between quantum and classical hardware, then we can say, okay, this is where quantum hardware outperforms classical one. This is the type of data that quantum hardware can deal better with and process, and which may lead to quantum advantage.
Okay.
Yeah, so
thank you very much.
Thank you.
Thank you.
All right. Let's move on. As you can see, the loss function is well conversion. And it is I believe that the model can do better. And I will leave you this one with the tasks. But let's move into the next visualization. So we need. So this is the example of the moon dataset. As you can see, the quantum hardware tried to bend over these colors in order to match the colors of the classes of the moon dataset. It did its best. It shows that it learned some patterns. However, you can see some points are in the blue region, some yellow points are in the blue region, and the blue points are in the yellow region. This means that we can do better with our quantum machine learning model, and I will show you in the task how you can do it. This is basically what we are going to do is to change the hyperparameters. So whether it will be like the number of layers, the encoding techniques, how many steps we do. So Having some summons. Right. All right, let's move on. Yeah, let's move on to our larger data set, which is the MNIST data set. So the MNIST data set is like, but I didn't show you an example of it. Let me check. Yeah, this is an example of the MNIST data set. As you can see, it is an images of handwritten digits like 0, 1, 2, 3 until 9. And in our example, what we are going to make stock sample and to limit our example into a binary example, we are going to filter. First of all, we import the necessary function, necessary imports. Then we import penny name, torch, SQLN for dataset. We load the dataset, and then what we are going to do, we filter the dataset. We only keep the 0 and 1 classes instead of having these 10 classes. From 0 to 10, we only take 0 and 1. This is the simplistic. We can go for multi-class classifier, but this one will require a lot of data sets, a lot of time to train, and too many qubits to measure. Right, so we filter the qubits for 2 binary examples. Then in order to reduce the data set, for the sake of time, we only take for trainable examples to be 10,000, and for the test example to be 2,000 samples. Next, we need to do standardize and perform PCAs. So as you can see in this example, so this example, this is an image which contain multiple pixels that describes this this digit. Yeah, so how much digit means how much features. In this example, like it will be 200, around 200 times 200 features, which is a large number of data sets. A large number of features, sorry. So what we are going to do, let me show you the example here. In this example, we only had two features. We needed 2 qubits. For this example, if we do the math, like I need to do the math right now. Okay, 200 times 200 pixels means we have 40,000 features. So we cannot have 40,000 qubits. So this is unpractical and impossible to do it. What we do is we reduce the dimensionality for simplicity. We reduce the dimensionality of this image. For instance, in our case, we took only 3 pixels, which means 3 features, which next translates to only 3 qubits. So this dimensionality reduction will only take the a transformation of the whole features and only describe it with only 3 meaningful features that describe this digit. So this is the PCA technique. For that, what we are going to do. So as you can see, these pixels are black until white. So the pixels values are between, if we normalize them, it will be between -1 and 1. So this is not a language of the quantum circuit or the qubits. So qubits speak with rotations. So instead, from going from -1 to 1, we do -pi to pi. So these are rotation values that we are going. We are going to multiply these pixels that are from -1 to 1, multiply them by pi, the value, where it is. smoothly put all the pixels from minus pi to pi in order to make them a useful quantum rotations instead of just classical values. We make them like, so to say, quantum values, like quantum rotations. Next, we are going to split the dataset from training datasets to test datasets with the labels I. Right. This is the classical part where when we load the dataset, after that, as I mentioned before, we move to the quantum part, which is the encoding plus the trainable parameter, trainable block. This is the example of lightning qubit. This is the lightning qubits, as I mentioned here, right? So this is an optimized version of the default qubit that we used before, which use like C++ high performance simulators for quantum circuits. So it is designed for faster and less memory computation. Of course, we need to define how much parameters we need based on the quantum circuits or the trainable block, ansatz or the variational circuit. So I'm using this interchangeably to familiarize yourself with it. After that, what we are going to do is here is the data encoding. So we use the angle embedding. So these are the built-in functionalities from Penny Lane. So instead of doing it from scratch here, so we are doing this manually. So this is what happened under the hood of angle encoding. We use a rotation of based on the features, or the rotation value are defined with the feature value. This function do the same, angle embedding, but it's much simpler and concise, as you can see from the template of the Penny Lane platform. For the trainable parameter, a trainable block, we use another template. So the other variety of the ansatz is the strongly entangling layer. So you can have different ansatz. You can create your own and test with your own ansatz. So this is the ansatz, and this is the embedding. As you know, we have some already defined embedding techniques: angle encoding, amplitude encoding, basis encoding. So you can keep that fixed. Choose one. However, you can play with the ansatz. Choose, for instance, different rotation types, different entanglements between qubits, whatever, be creative. This is just an example. Add many layers. So the layer is, for example, is how much time you repeat this block. So for instance, we have one layer, we got only this block. Two, we repeat this block 2 times. This also will increase the number of parameters. All right. Train. Yeah. So as you saw, we are trying to make to define this quantum node and transform it into a torch layer. So what does this mean? So I'm trying to integrate the Penny Lane platform with the torch platform to make use of the torch functionalities, like the loss functions that torch allow us to use, or the accuracy evaluation functions. So all that you need from the classical parts you are familiar with, you can use it with quantum layer. So as you can see, because what we are doing here, we are moving from the quantum layer to the classical layer again. So the classical layer, we can rely on torch library in order to compute the loss function and do evaluations. Here we, so for this quantum node, what we're doing, we're telling that for the interface we're using torch. For example, if you are familiar with TensorFlow, you can use TensorFlow here. For the differentiation, for like computing the gradient descent, for differentiation of the quantum circuit, we use the parameter shift rule. Also, you have like the adjoint technique. So the adjoint technique is only what it does do. What it is doing is trying to do backpropagation throughout the quantum state of the quantum circuit. So this is a simulation. We cannot do it on the hardware because once you measure at the end the quantum state, you cannot go back and re-access the same quantum state because at the measurement, at the measurement, we collapse the quantum state into whether to be 0 or 1. So this collapse thing would not allow us to do like backpropagation to re-access the quantum state again. We cannot do this. We can only do it in the simulation if we are doing simulation, which is we can use the adjoint. The adjoint is much faster for computing the gradient of our quantum circuits. However, for real hardware, we need to use quantum parameter shift rule because it makes it simple. What does it do? It makes it simple and harder to compute. What does it do? It first do a copy of this circuit 2 times. It computes 2 times on the quantum hardware. And so the first circuit have parameters shifted backward with pi over 2. And the second quantum circuit, it have parameters shifted onward or forward by pi over 2. And we take the difference between the results from the measurements and divide by 2. And this is the result of the differentiation over the parameters. So this way, we are not going through the same circuit. We are creating a copy of the circuit, run it 2 times, then compute the gradient. Yeah, so most of the time we are going to use parameter shift rule for computing the gradient and doing optimization of the parameters. Yeah. Next,
وليد
we're trying to yeah.
بس عنده سؤال، اتفضل حسن.
اتفضل.
حسن اتفضل يا حسن.
No, we can't hear you.
Do you hear me now?
Yeah, now we can hear you.
Yeah, I mean the last layer, if there is a layer is classical, how it's upgrade its gradient, and there is layer before it which is quantum.
Yeah, this one, the quantum circuit. We define the quantum circuit first, right? And then there is the classical layer. So the classical layer, going to use the optimizer like Adam optimizer. The Adam optimizer rely on gradient, computing the gradient of the loss function with respect to the parameters of the quantum circuit, right? For this, we are using the parameter shift rule in order to compute the gradient of the quantum circuit to help the classical classifier or classical optimizer to do optimization. So this is all about the parameter shift rule. I didn't include the details of how we compute the parameter shift rule mathematically, but I can share with you some resources about it after the lab session. And also I'm sharing some at the end of this lab, of this notebook. Okay?
Okay, thank you, Walid.
All right, you're welcome. All right, let's move on because we're already in 1 hour. So what we are going to do, we define the evaluation function for in order to evaluate the performance of our model. how many epochs. So we are using, for this case, we are using mini patch training, as this is a little bit complex example compared to the first one. For this, we are doing epochs instead of steps. So yeah, I'm already trained this example, as it may take like 17 minutes. So yeah, as you can see, the model doing quite well at conversion, but not that much like better than as we saw in the simplest case. And I will show you how we can make the model more performant throughout the tasks. But beforehand, let's do some visualization and familiarize ourselves with some of the evaluation metrics. Like this example, this is a confusion matrix. And what says we have like true labels with predicted labels, the axis, y-axis and x-axis. For the label 0, for the data, for the samples that have class 0, the true one with the predicted, we have 572 samples that been predicted to be class 0. The same for class 1, we have 928 that have the right class, right? So this is the predicted label, this is the quantum prediction. This one is the reference, the label. This blue and this pink colors means that our model did false predictions. As you can see, they are quite high, but we can. This is explainable because we only have like 75% of accuracy for test accuracy. But we can use techniques in order to make this higher. So another evaluation technique is that we plot the receiver operation characteristic curve. So what does this curve show? So this orange line means how a random classifier would perform. So this is a random classification. So like a 50-50, right? However, this line, the blue line, is the our model. So what it is is doing higher than the random classification. So as you can see, it do much better than the random classification, but the model needs more. There is room for improvement. Actually, so I will show you how we can do this to improve the model. Let's skip this part and move on to the tasks. So yeah. So let's go through some general rules for this task. And the main reason or the main goal of these rules is to familiarize yourself with the different hyperparameters, specifically from the quantum part. I'm not sure if you are familiarized with the classical hyperparameters, but I'm going through them both, so you can have a clear vision over them. All right, so let's go through the first task. This will explain the shots with sampling noise. Yeah. So as I mentioned, in this example, we're setting the number of measurements or the number of shots to be 8,000. I want you to go through from 100,000 or 100 until 10,000, right? And what we're going to do is to plot the accuracy versus how much shots you do. Yeah, so this is the task. So explain this analytical differentiation. No, this is the other one. The first one I just explained to you. If you set the shot to be none, which will be an analytical differentiation versus a sampling differentiation, right? Yeah, you are going to set the shot to be none and also set the shot to be 8,000. So you are comparing here, speaking about this part, right? Both these lines. So you are going to run this example 2 times. The first one, you comment this line and uncomment this one and run the analytical mode. then see the accuracy, note it, like save it, then run again this example. However, this time you are going to use the noise or the probability computation, right? So the noise mode. Then note this accuracy and compare with them and see, and then add your comments. What do you remark and what are your conclusions? So yeah, this is A2. This one is the one that I told you. The first example is to go from 100 shots until 10,000 shots or measurements, and see how the measurements make the results better. Because if you just took a smaller number of measurements, then your result gonna be have more noise and have more uncertainty in its results. So what you're going to do, you are going to increase this number of shots and conclude whether this higher number of shots will reduce the noise of your computation or not. This will be like apparent from the accuracy versus the shots plot, right? So I need to use some colors here because they are not clear. However, I'm going through it. They can make it clear for you. So, right. Yeah, so this is this kind of parameters are the quantum parameters. So this A section is for the quantum hyperparameters that you are going to change. For the second one is for the classical parameters. As you can see, the quantum model doesn't have only quantum hyperparameters, but also classical hyperparameters that can contribute to the model performance. Right? So for this example, for B section, you're gonna change the step size values going from 0.05 until 0.4 and see how the model, the quantum machine learning performance get affected. So just try to plot a table with final train and test accuracy. See also the mean train loss, which one that achieve lower convergence. And yeah, conclude and give an exam, your opinions or your remarks. For this one, I'm going to quantum hyperparameters. So what we can also do in order to improve the accuracy of the quantum model, we increase the number of layers, as I mentioned here. So this example has only one layer. So we need to use more layers. Because why? So this is classically also intuitive, because if you use more layers, you are adding more parameters. This way you are adding the expressibility of your circuits and making the model flexible with more parameters to learn more patterns from your data sets. So this is one hyperparameter that you can vary and plot the results. So same thing, like plot the test accuracy versus the snapshot, like how many layers, accuracy versus different layers. So we go through from 1, 2, 3, as many as you want, based on how much time you have, because you need to wait for the optimization process. As I mentioned, for the simulation, it requires much time for simulating the quantum circuits. Yeah, so take this in mind. Yeah, and discuss the expressibility versus overfitting Barn plateau. So because if you have like fewer parameters, you may at the end have like some overfitting of your data set. We need to increase this expressibility of your circuit in order to make it more reliable and not overfitting your data set. And this way, your model can learn more features and more patterns from your data set. And at the test phase, can recognize to classify better the classes of your data set. Right? So D section is also another quantum layer. So as I mentioned, you are using different encoding techniques, whether it would be like angle encoding, implicit encoding, or basis encoding. Most cases for quantum machine learning, we use whether an angle encoder or amplitude encoding, because they are both doing better at like the trade-off between the number of qubits and the depth of the qubits. So which is the depth and the number of qubits. So there is two parameters that describe the quantum circuit. The first parameter is the depth. So how much layer you have in your quantum circuits that run parallel. So in this example, we have 1, 2, 3, 4. So the depth of this quantum circuit is 4, and the width for this circuit is 2, because only we have 2 qubits. Then if you use the basis encoding, so this is not efficient in the width, but efficient in the depth. So if you use basis encoding, you may need like 10 qubits, but only one depth of your circuit, only one layer. For angle encoding, we only need 2 qubits for this case. But because we only have 2 features, this is a sample example. If we have like let's say 200 features, so this will be the example for you for the MNIST dataset. What we are going to do instead, for me, I just took 3 features. I reduced the image into 3 features. For in your case, you can take 10 features, because the more features you take, the better. It helps the model learn more features in your example and perform better. Right? So exactly. So this is your another task that you are going to do. So instead, take 10 qubits. This way, you are going to take 10 features, right? But it will take much longer, because you are simulating 10 qubits. What you can do is you check 10 features, right? Let's forget about qubits, the number of qubits. Actually, this should be the number of features instead, saying the number of qubits, because if we change the encoding technique, the number of qubits will change too. In this case, it will be should be 3. Right? Can ignore this one. All right. In the example I told you, take 10 features. You cannot, if you want, you can go through the angle encoding. So for each feature, you give it 1 qubit. However, you can use another technique, which is the amplitude encoding. But the amplitude encoding allow you to encode 2 to the power of n features. So n is the number of qubits. So for this 10 qubits, you may need only 2 to the power of 4. You may need only 5 or 4 qubits to encode these 10 features instead of 10 qubits in case of angle encoding. Yeah, so this is the encoding choice that you can change. Finally, this is finally you can use the template of penny lane. Let me show you. I guess I linked it. Yeah, this one. I guess you cannot see my screen, but I will share it with you. Okay. Share it.
ممكن ناخد
It's a
سؤال
different
طيب
penny lane. Yeah, I will just 1 minute. I will finish. I'm about to finish. Then you can go for questions. Okay. Thank you. So so for the templates, you can use the penny lane templates to make it easy and concise for you. For instance, for different ansatz, you can use different ansatz given from the penny lane platform. For instance, you can compare the strongly entangling layer ansatz with the basic entangling layer. So this is another ansatz from the penny lane template. So I want you to do, this is a task for you. I want you to change, to change this trainable block with different architectures of ansatz and compare and see if the architecture really matters in quantum machine learning performance. Right, I guess this is the end of the notebook. Right, these are some resources, and I can share more throughout the week, so it can help you more. Then we can go for question here, please.
إيناس اتفضلي.
Okay. Assalamu alaikum. First, I would like to thank you, Dr. Walid, for your presentation. It was very helpful. I have actually two questions. My first question is from your explanation about the amplitude encoding. You said that we take 2 power in the number of qubits. So from that we can understand that amplitude encoding is better than angle encoding because it takes more features, right?
It needs fewer qubits, so it is better in this sense.
Fewer.
It needs only it needs only fewer qubits. However, in some cases, if you use angle encoding, the quantum machine learning will perform better because in this way you are encoding each features in each qubit. For amplitude encoding, yes, it do kind of mix. It mix the features with each other. In some examples, make it harder for the quantum machine learning model to perform better. So in sometimes we require to get angle encoding. So this is why I give you these tasks in order to do benchmarking to see which set of settings is better for this type of data set. So for each data set, you can gonna say, okay, for MNIST data set, it is better to use amplitude encoding with this type of ansatz and with this number of shots, number of measurements. So this is your way to understand how the quantum machine learning model perform under the hood and how you can build an intuition how it works.
Yes, I understand. So we can relate the number of states. Can we relate the number of states of the qubits to the number of features of the input features?
The number of states. So let's make it this way. So the states, the quantum circuit can be described as a quantum state, one quantum state. You mean the qubits. So the features for the angle encoding, for each feature, it corresponds to 1 qubit. So if we have 2 features, we're gonna have 2 qubits, right? For angle encoding, we rely on this relation. For instance, let's say we have 2 qubits, right? If we use amplitude encoding, then 2 to the power of 2 equals 4, right?
Yes.
So we are going to encode 4 features into only 2 qubits. So this is amplitude encoding. For angle encoding, for these features, we need 4 qubits. So this is how you can compute it.
Okay. Yes. Okay. Also, from the task you asked us to perform, we can conclude that the building or constructing the circuit of the quantum, it's not based on standard or specific type of calculation. So does it have a type of black box as also in the deep learning and the neural networks?
You can deem the quantum circuit as a black box, but if you do it manually, you know what you're working on. So for the first case,
yeah, so it's easy to calculate it for the first case, but for the images, especially in the images data.
Yeah. So which one? Which your question? Could you repeat?
Yes, I mean that if I use, for example, 10 qubits on a classification of images data, if I use this number of qubits, it will be hard to explain the type of the circuit or each each gets a rule. So it will be like has a type of black box. That's what I mean. The big circuits or the complex circuit of quantum.
So you mean it's not kind of like black box, because if you get much qubits, it make it harder for the only the classical hardware to simulate. And if you use that 10 qubits on the quantum hardware, it also kind of not straightforward, because 10 qubits will lead to more noise. This way, your performance gonna degrade, and degrade in a way that noise gonna affect the performance accuracy of your model. In case of like using 2 qubits for simulation, the same as using 10 qubits for simulation.
Yes.
The problem is that with simulation itself, it gets more harder to simulate. So it's
because it will take more
dimension
time, you mean?
because the dimension of the example of the simulation or of the matrices in your circuit gonna get larger to the power exponentially
Yes.
faster. So this is why it makes it too hard for the simulation to simulate the quantum circuit itself.
Hard in which direction?
Multiplying the matrices, because you have if you get
The gates.
like 10 qubits, if you got 10 qubits, then you're gonna have 2 to the power of 10 matrices dimension to multiply with them. If you got what I mean.
Yes,
You have
but
a larger matrices to do multiplication. So this is itself a harder problem to solve.
yes, I understand. But I mean also if I use like more complex images data, like for medical images, for example, the pixels and the structures of the image is very important. So it need more features to input to the quantum model itself. This is my idea about using a lot of qubits.
Yeah, this is what we are doing at the moment. We can't use. You can use it if you have a high performance hardware to simulate, and it is better to have, as you mentioned, to have more features. It makes it more easier for the quantum model to learn more patterns between the features and process the data set more efficiently.
Yes,
However, for toy examples, like this one for MNIST dataset, where you can go see for in the literatures, they first validate their results with the MNIST datasets, because it is easier. You can use the PCA. Only few features help the model to converge. However, for complex datasets, for breast cancer datasets, the correlation between the features get more complex, and this time we need more features.
Yes. Okay, I understand. Thank you very much.
And one more thing, for pre-processing the dataset, this is also a very important part, because if you pre-process your dataset the right way, it's gonna help at the end your quantum machine learning model to converge better. This way, this is why you use like different dimensional reduction techniques beside PCA in order to make the correlation between features.
We use the hybrid quantum classical models.
True. Yeah,
yes.
Exactly.
Okay, thank you very much, Dr. Walid.
Thank you. You're welcome.
لو
I'm
حد
going to
عنده
share
سؤال
with
تاني اتفضل.
Yeah. You have any question? yeah, feel free. Otherwise, I will share with you this notebook and for you to practice it. And if you have any question, actually, I try to use because a more realistic way to do this example is to run it on the quantum hardware. Unfortunately, due to time, I had some problems accessing my account. I couldn't connect with the hardware, the IBM quantum hardware, due to some issues with the connection. I tried with different accounts, but it didn't work. Yeah. So one more thing to tell you, because you're gonna go through a lot of issues. Of course, you can go ask ChatGPT. However, if ChatGPT didn't help you, there are some platforms like Penny Lane platform that's where developers of the Penny Lane library itself can answer your question about any problem you face. Also, there is Qiskit Slack channel where they also have these developers of the Qiskit library. They can answer any question that may you may raise any issues with running your examples or access using any features, any function from their library. You can ask them. I will share the links of these platforms, and yeah, you can use it for your project developments in the future. All right. Was that clear? Any other questions? Meanwhile, this is my email. If you have any questions, any concerns, just contact me here.
اتفضلي يا دكتور على طول.
في سؤال excuse me. How are you sharing the notebook?
I will share the link for the Google Colab with you on Discord.
On the chat here?
On the chat. I guess, Ahmed, do you have their emails so you can send them?
هيكون صعب لأن السمر سكول مفتوحة، يعني مفيش تسجيل معين مختلفة عن الهاكسون بتاع سبتمبر، هتبقى ناس معينة معاها البيانات بتاعتهم. لكن ممكن نبعت اللينك هنا وعلى الجروب الرئيسي على الواتساب. دي طريقة تانية، ممكن لو تعمل لنا داونلود مثلا ونحطها على لينك الدرايف، ده برضو اوبشن تاني.
All right, okay. So I guess it would be better to share it here. Share this with you. Copy link. Otherwise, if you have their contact on WhatsApp, you can share this link too with them.
Okay, there is option, there is a file option. You can download the notebook and then you can send it on the group if you can.
Sure, yeah, I can. Just I don't have the access to the group, but I will share it with Ahmed. He can forward it to you.
All right.
أنا بعت اللينك دلوقتي حالا على الجروب الرئيسي، مش مشكلة.
No, I mean this link will always like send you a permission to accept the permission. But
no, this is for public, I guess. You can access, anyone with the link can access it.
هو مفتوح وأنا جربته بالفعل، مفيش مشكلة.
Fine. Okay. I had another option, but it's fine.
Yeah. This option also, you can download this file and run it on your local hardware instead of.
Yeah. I wanted to do that, but it's okay.
Sure. Yeah.
حد عنده أي أسئلة تانية بعد اللاب الشيق ده؟ طيب، واضح بقى إن الناس خلاص سألت واستمتعت بما فيه الكفاية. الصراحة أنا كنت يعني مستمتع جدا، لاب لذيذ. أشكرك يا وليد.
شكرا.
يعني متشوق اكتر ان انا اقابلك بقى في الهاكسون بتاع سبتمبر، واظن برضو كل الناس يوافقوني الرأي هنا اللي هيشارك في سبتمبر. برضو دكتور وليد هيبقى معانا، وبإذن الله هيبقى هاكسون لطيف.
Of course, looking forward to it. يعني مبسوط أكون معكم هنا. بدي أشوفكم في next week maybe in 3 years. Next week we see each other.
طبعا لو مصر هتنور. اتشرفت بيك يا وليد، شكرا
لا
لكم على
لا،
السيشن
شكرا.
وشكرا ان انتوا قعدتوا معانا.
شكرا لكم كثير.
كده بقى نبقى خلصنا اليوم الثالث. ألف شكر يا وليد تاني.
Alright. Okay. Right. So have a good day. Have a good night. Thank you very much. Bye.
أشوفكم بكرة بقى يا شباب، مع السلامة.
هو في حد لسه فاتح هنا ممكن أسأله على كام حاجة؟
بخصوص سمر سكول.
هو أنا أول مرة أحضر يعني خالص، فمش فاهم الدنيا ماشية إزاي أو إحنا كنا بنعمل إيه بالظبط. يعني أنا عجبني جدا السيشن فقلت أقعد أسمع،
اوكي.
فكملتها للآخر. بس أنا مش فاهم بقى يعني أنتوا بتعملوا إيه بقى في الآخر، يعني بتوصلوا لإيه؟
ماشي. انت خريج ولا لسه طالب في الكلية؟
أنا خريج.
خريج ايه؟
أنا خريج كلية علوم، وكنت بدرس تراك داتا ساينس مع ناس اسمهم ALX أفريكا، وكملت معاهم للآخر ودلوقتي شغال داتا ساينتست في شركة كده.
نايس، حلو ما شاء الله. ماشي، هي السمر سكول دي مينلي يعني في الكوانتم كومبيوتنج. تمام. يعني احنا البيز بتاعنا اللي احنا بنتكلم عليه الكوانتم كومبيوتنج. تمام. فدي كانت سيشن كوانتم ماشين ليرنينج.
اوكي، فيري نايس. انا اصلا كنت متحمس قوي عشان انا شغال اصلا ماشين ليرنينج، ف يعني عجبتني الفكره. بس انتوا مكملين كوانتم كومبيوتنج كامل بقى، مش بس ماشين ليرنينج بس، صح؟
اه، يعني الكوانتم ماشين ليرنينج ده سكوب واحد من ضمن السكوبس بتاعت السمر سكول. يعني احنا امبارح كان عندنا سيشن ماشين ليرنينج كلاسيكال، وقبلها كان عندنا زي انترودكشن كده للكوانتم كومبيوتنج. تمام. بكره عندنا الكوانتم اوبتمايزيشن ستيب برضو فيها شغل ماشين ليرنينج، فممكن تحضر بكره عشان تكمل بقى يعني اللي انت خدته النهارده بقى على بكره. فاهم؟ بس هو السكوب بتاع السمر سكول اللي هو الكوانتم كومبيوتنج. هو طبعا السيشنز بتاعتها مش يعني بنحاول نقرب لكم، نديكوا اوفر فيو، نديكوا لابس كده سريعه عن الموضوع. تمام. بس طبعا انت لو عايز ان ديبث بقى ده موضوع مختلف. بس انت في الاول يعني محتاج تعرف ايه الكوانتم كومبيوتنج، تعرف ايه فكره الكوانتم اصلا احنا ليه بنستخدمه. في الحته بتاعت الماشين ليرنينج بقى لازم تعرف تريليت بين الكيوبيت وما بين بقى شغل الفيتشرز وشغل الداتا بتاعك. فقول لي كده، انت عندك اي سؤال يعني بخصوص السيشن مثلا، او ولا عايز تعرف مثلا رود ماب للموضوع ولا؟
هو انا كنت بدرس كوانتم في الكليه. يعني انا اصلا تخصصي في الكليه كان كيمستري،
اه، حلو.
فكنت بدرس ميكانيكال كوانتم ميكانكس كتير يعني. ف فاميليار شويه مع فكره الكوانتم والسوبر بوزيشن، وليه بنستخدم باي بدل 1 and zeros علشان دي رقم بيدي infinite number of states like the quantum qubit نفسها. فانا فاهم شويه ليه اختار ان كل كوانتم تكون فيتشر. يعني كل فيتشر بيختار، وفاهم شويه هو ليه اشتغل البي سي اي عشان حد يصغر عدد الفيتشرز اللي معاه في السمبل الصغيره ويحطها جوه كل واحده جوه كيوب. ده اللي انا
مم.
فهمته. الاساسيات بتاعت الكوانتم كبروجرامينج مش ما خدتش اي سيشنز عليها قبل كده، فالحاجات دي ريكوردد مثلا ممكن ابص عليها.
هي ريكوردد ان شاء الله، يعني هننزلها، وان شاء الله برضو يعني هيبقى عندنا كده تشانل على الواتساب جروب كده للريسورسز برضو. آه بس يعني وعندنا اخر يوم في السمر سكول في الكوانتم كيمستري، فاحضرها بقى عشان تلنك كل الداتا اللي معاك دي في السيشن دي ان شاء الله.
حلو جدا، حلو جدا بجد. طيب هو في قال تقريبا ان في ديسكورد شانل غير الجروب الواتساب، ولا اكمل في جروب الواتساب عادي اركز
لا لا،
معاه؟
خليك على جروب الواتساب عشان هو موستلي يعني الليتس ابديت يعني بتنزل عليه. الديسكورد احنا عاملينه بس عشان عشان الهاكاثون بتاع سبتمبر ان شاء الله. فميلي يعني مش هيبقى فيه ديسكورد في سمر سكول، بس تابع ميلي على الجروب الواتساب، واحنا ان شاء الله كل الماتيريال واللابس والريكوردد سيشنز هننزلها على الدرايف وهنبعت لك اللينك ان شاء الله.
حلو جدا. طيب الهاكاثون ده ممكن الناس تخش فيه عادي، ولا هو لازم يعني انا ما مسجلش في اي حاجه ممكن اسجل لو كده، او ولا خلاص الباب قفل؟
هو للأسف الباب قفل خلاص يعني. أنا يعني من شهر 6 وإحنا شغالين في موضوع الهاكاثون ده، فللأسف باب التقديم قفل. بس إن شاء الله يعني هيبقى في هاكاثونز تانية وفي سمر سكولز تانية إن شاء الله، فتابع بس على الواتساب جروب، وكل فترة كده هتلاقينا إن شاء الله عاملين إيفنت يعني.
اوكي حلو جدا. خلاص تمام، انا هتابع برضو لو في اي هاكاثونز تانية ان شاء الله، هكون يعني هبقى مبسوط لو دخلتها.
طبعا ان شاء الله باذن الله، يعني دايما كده ربنا يكرم اول هاكاثون ده يعدي على خير كده ان شاء الله، وباذن الله
طب هو
الهاكاثون.
هيبقى يقدر يعني اقدر اجي بس حتى اتفرج كده اشوف البروجكتس اشتغلوا الناس على ايه، ولا مش اكسسبل للناس؟ هو اصلا
هو
اونلاين في مكان كمان يعني، ما اعرفش اي حاجه بجد، معلش.
هو هو الهاكاثون هيبقى ان بيرسون في مكتبة اسكندرية. والمشكلة ان هو ليميتد يعني للناس اللي هتحضر اوف لاين. كان في اصلا يعني كان عندها سelection فيزز كتير يعني لحد عشان هم 30 واحد بس اللي هيشاركوا. فبس هو ان شاء الله هيبقى لايف يعني. هنحاول يعني نعمل له بودكاست لايف كده ان شاء الله على اليوتيوب او حاجه، وهنبلغكم برضه على الواتساب جروب بحيث ان انتوا تحضروا كل السيشنز والتوكس اللي هتبقى موجوده في الهاكاثون برضه.
حلو جدا تمام. طيب هو اخر حاجه، هو في فيز معينه للهاكاثون بعد كده، او ان انا لو عايز اجي احضر بقى وكده، ولا يعني
آه،
اعرف كانت ماشيه ازاي بس؟
بص هو احنا يعني الجروب بتاع الكوميونتي اصلا بتاع الكوانتم كومبيوتنج في مصر تمام، فاي حد هيعمل اي سمر سكول، اي حد هيعمل اي هاكاثون، اي حد هيعمل اي ايفنت من اي نوع يعني، هتلاقينا بنعمل اناونسمنت على الجروب على طول ان شاء الله. تابع بس معانا على جروب الواتساب كده ومتقلقش.
اوكي
كان
حلو.
كان ميرنا 25 كان يو ادفايس وذ رود ماب. طب عايزة رود ماب لإيه بالظبط؟ حاجة معينة في الكوانتم ولا مين يعني بشكل عام؟ ماشي طيب. عامة هي ممكن تكون خرجت من السيشن أو حاجة. عامة هبقى إن شاء الله على الجروب الواتساب برضو ممكن نبقى نبعت لكم رود مابس. يعني to the field interest in quantum machine learning. اوكي طيب. طب انت عندك اي باك جراوند في الماشين ليرنينج او في السوفت وير عامة، او في الفيزيكس او في الماثماتكس؟ يس طيب ممتاز ممتاز ماشي اوكي. هشير معاك ان شاء الله الكوانتم ماشين ليرنينج رود ماب. وعامة الكوانتم ماشين ليرنينج يعني لسه في بدايته، يعني هو مش قوي جدا زي الماشين ليرنينج نفسه يعني الكلاسيكال عامة في أغلب اليوز كيسز بيبقى هو أفضل من الكوانتم، بس هو الكوانتم عنده شوية أدفانتج كده زي موضوع الفيتشرز وزي موضوع الانتليجنت يعني سوبر بوزيشن والانتليجنت. بيساعدوا في شوية بروبلمز كده. فهو لسه يعني في طور التطور زي ما بيقولوا، يعني لسه في مرحلة الار ان دي يعني. فهيبقى ستارت حلو قوي لو انت اوريدي عندك باك جراوند في الماشين ليرنينج انك تدخلي في الكوانتم ماشين ليرنينج. بس هبعت لكم على الجروب برضو رود مابس لكل التخصصات بتاعة الكونتنت إن شاء الله. و يعني تابعوا على الواتساب جروب، أهم حاجة هو الواتساب يعتبر هو أكتر حاجة فاليد يعني، لحد ما إن شاء الله ربنا يكرمنا كده ويبقى عندنا بلاتفورم أو حاجة. في حد عنده أي أسئلة تانية؟
تمام، حلو جدا. هو سؤال أخير، هو في أي ريسورسز تقدر ترشحها لي لتطبيقات الكوانتم ماشين ليرنينج في الناتشرال لانجويج بروسيسنج ولا
آه،
ما؟
بص هو ميلي يعني يعني هبعت لكم على الجروب كده النهارده الريسورسز اللي معانا يعني او اللي موجوده، بس هي ميلي هتلاقيها بيرز وهتلاقي اي بي ام. يعني لو دخلت على اليوتيوب كده هتلاقي اي بي ام كيسكت او تشانل اسمها كيسكت، هتلاقي فيها ريسورسز كويسه جدا اذا كان الكوانتم ماشين ليرنينج او دي. بس موست لايكلي اغلب الحاجات هتلاقيها بيبرز منشوره. تمام، وهتلاقي بقى يعني تشانلز على اليوتيوب كتيره جدا بتتكلم في الكوانتم ان ال بي. ف
اوكي، كويس.
ان شاء الله هنعمل لكم يعني تشانل كده على الواتساب جروب فيها ريسورسز يعني، عشان برضو الناس اللي مهتمه والناس اللي بتسال. وانا مبسوط والله ان العدد بيزيد، دي حاجه كويسه يعني، خصوصا ان الكوانتم يعني كاتنج ايدج تكنولوجي وكل العالم لسه بيبدأ فيه بشكل ما يعني. تمام، هو اهم حاجه في الماث اللينير الجبرا عامه. لو عايزين تديك ديب شويه بعد اللينير الجبرا بقى تخش في الجيومتريك لينير الجبرا وكده، بس دي حاجه ادفانسد شويه. بس هو مينلي المهم في الرياضه اللينير الجبرا. بس شكرا يا شباب يعني، وإن شاء الله نتقابل تاني، نتقابل بكرة إن شاء الله على خير، وتابعوا على جروب الواتساب إن شاء الله، وهنزل لكم الريسورسز والرود مابس وكل حاجة. آه،
شكرا.
ماشي. عامة سارة يعني حتى لو ما عندكيش أي باك جراوند في الماث أو في أي حاجة يعني، ممكن تبدأي من أول جديد عادي، مفيش مشكلة. هنبعت لكم الرود ماب إن شاء الله. السلام عليكم.
عليكم السلام.